For centuries, the night sky has been a place of calm and order. Stars rise, stars set, and for the most part, they shine steadily, faithful beacons across human history. But in 2015, astronomers noticed something that broke the pattern. A star nearly 1,500 light-years away that flickered like no other. Sometimes it dimmed by a few percent, sometimes by nearly a quarter of its light, like someone was drawing cosmic curtains across its face. The usual explanations, planets, comets, dust, didn't quite fit. Some even dared to whisper, could it be something artificial? This star, now known as Tabby's star, became the most mysterious object in the galaxy, a puzzle that continues to challenge everything we thought we knew about the universe. The star that blinked at us. NASA sent the Kepler Space Telescope into space in 2009. Its simple but powerful job was to look at a part of the sky and find tiny dips in starlight that could mean there are new planets. The idea was easy to understand. If a planet went by its star, Kepler would see the light dim for a very short time, like someone turning on and off a light switch. These dips are small, expected, and happen over and over again for most stars. When seen from far away, Earth makes the Sun less bright by less than 1%. Jupiter would make the price drop by about 1%. Until scientists found Tabby's star, the star that wouldn't follow the rules, everything fit into neat designs. Tabby's star is an ordinary F-type star in the constellation Cygnus, roughly 1,500 light-years away. On the surface, it should be boring. Stars like this are stable, middle-aged, and shine with reliable brightness. But in the data collected by Kepler, something was off. Instead of the gentle, repeating dips of a planet, this star plunged in brightness by as much as 22%, then brightened again, then dipped irregularly at different times. No rhythm, no clear pattern, just chaos. It was as if a cosmic hand kept flipping a dimmer switch in unpredictable ways. The first reaction among researchers was disbelief. Maybe the data was corrupted. Maybe the telescope glitched. Kepler wasn't perfect. Stray pixels, cosmic rays, or small malfunctions could mimic dips that weren't real. But after checking, rechecking, and comparing, the odd light curve held up. Other stars in the same field looked fine. The telescope wasn't broken. The anomaly was real. Tabby's star really was flickering, like no other known star. This kind of dimming was shocking. A gas giant planet passing in front of a star could only account for a dip of around 1%. To get a dip of 20%, you'd need something enormous, bigger than Jupiter, bigger than any planet in our solar system. Worse, the timing was completely wrong. Planets orbit regularly, so dips repeat. But here the dips showed up randomly, sometimes short, sometimes long, sometimes clustered, sometimes months apart. The light curve looked like static on a screen. Astronomers tried to fit it into familiar categories. Could it be an eclipsing binary system, where another star crosses in front? No, the dips weren't deep enough, and the spectrum showed no sign of a companion star. Could it be a giant planet with rings like Saturn, tilted in just the right way? That would explain one dip, maybe two, but not the dozens of irregular ones. Was the star itself unstable, pulsing and fluctuating? F-type stars don't behave that way, and the changes here were far too dramatic. Every usual explanation fell apart under scrutiny. The star earned a nickname, Tabby's star, after Tabitha Boyajian, the astronomer who led the first detailed analysis. But the public gave it another title, the most mysterious star in the galaxy. By 2015, its bizarre behavior was making headlines everywhere. The mystery was irresistible because it poked at a question humanity loves to ask. What if this is evidence of something artificial? People jumped to that conclusion because they thought that if natural theories didn't fit, then smart ones might. It would be normal for the light to drop by 20% if a huge object went by in front of the star. So the idea of an alien megastructure like a Dyson sphere or a group of collectors came out of nowhere. Scientists were careful, but the people had a great time with it. Overnight, Tabby's star wasn't just a strange event in Kepler's data, it became a big deal in pop culture. But before the theories of aliens could take over, astronomers kept grinding through the numbers. They looked for repeating cycles. They tried to model dust clouds, shattered comets, warped disks, and planet-sized debris fields. They even pulled out old photographic plates from the early 1900s to see if the star had been fading for a long time. To everyone's surprise, it looked like the star had indeed dimmed over the past century by about 15%. The mystery only deepened. Kepler's job was not to solve mysteries, but to create them. It provided the raw light curves, the jagged lines that showed how much brightness reached its detectors. For most stars, those lines were neat and regular. For Tabby's star, they looked like a lie detector test gone haywire. Astronomers who studied variable stars, eclipsing binaries, or transiting exoplanets had never seen anything like it. Some even called it the WTF star in early papers, shorthand for "Where's the flux?", because its light output defied logic. This was the kind of problem that anyone could understand, so the excitement went beyond the professional world. You didn't need a PhD to figure out what was going on. You could look at the map and say, "That doesn't seem right." There were also real people in the story, like an astronomer, a group of helpers, and a star that was acting poorly. This wasn't a faraway cosmic mystery. It was just one point of light in the sky that we could see. It was a star, but it dared to blink at us in a way we couldn't explain. Tabitha Boyajian's discovery. A scientist looking through a huge telescope on top of a mountain is usually what comes to mind when someone thinks of a major scientific finding. But Tabby's star's story began in a much less exciting way. Kepler was able to gather a huge library of digital light curves. For years, Kepler kept track of how bright more than 150,000 stars were every 30 minutes for almost 10 years. The data was like an ocean, and there was a strange, jumbled pattern in it that no one could quite understand. Tabitha Boyajian, an astronomer at Yale University at the time, became the face of the star's mystery. She wasn't the first person to notice something odd in the data. That credit goes to the volunteers at Planet Hunters, a citizen science project where regular people helped scan Kepler's observations. But she was the one who looked at the evidence carefully, realized it was unlike anything else, and took the risk of writing it up in a scientific paper. Boyajian's work began when Planet Hunters flagged Tabby's star as bizarre. The volunteers had been trained to spot the smooth, predictable dips caused by planets. Instead, they saw wild plunges, some small, some gigantic, with no repeating pattern. At first, even Boyajian thought it must be an error. Kepler's instruments were sensitive, and she had spent enough time in astronomy to know that strange glitches often mimic exciting discoveries. But the more she investigated, the harder it became to dismiss. Other stars observed by Kepler in the same field looked perfectly normal. Only this one star seemed to be misbehaving. Colleagues were called in, the calibration was checked, and the data was put through a number of different reduction processes. The dips were still there each time. The star switched on and off. Why was the question Boyajian and her team were sure of themselves enough by 2015 to put out a study in the monthly notices of the Royal Astronomical Society. Planet Hunters 9, Tabby's Star, Where's the Flux? Was a dull title. But inside the paper was one of the most puzzling in modern astronomy. Boyajian carefully outlined what the star was not. It was not a binary star system with another star blocking the light. It was not a planet with rings. It was not a dusty disk like the ones around young stars. Tabby's star wasn't even young. It was a mature, stable F-type star, too old for leftover planetary debris disks. In short, all the obvious explanations failed. What remained were long-shot ideas. Maybe a swarm of comets, maybe debris from a shattered planet, maybe something we had never seen before. The publication of the paper was just the beginning. Once the scientific community learned about it, ideas flew in from every corner. Some were grounded in astrophysics, others ventured into speculation. And then came the headline that pushed Boyajian's name into global media: Alien Megastructure. It's important to note that Boyajian herself never claimed aliens. She was careful, conservative, and scientific in her approach. Her paper ended with natural explanations, not science fiction. But other scientists, like Jason Wright at Penn State, suggested that if you were looking for signs of alien engineering, this kind of odd light curve might be the place to start. From there, the media frenzy took off. Tabby's star, named in her honor, became the WTF star, and then the alien megastructure star. Boyajian suddenly found herself at the center of one of the most high-profile astronomical debates in years. Her job didn't end when she published. Boyajian was also in charge of keeping an eye on the star. Once Kepler's mission was over, the dips could only be seen with instruments on the ground. Time on these instruments, on the other hand, is expensive and hard to get. Boyajian didn't wait for the government to give him money. Instead, he turned to crowdfunding. She made a Kickstarter effort called The Most Mysterious Star in the Galaxy and asked people to help pay for more tracking. There was a huge reaction. A lot of people gave money, and it raised over $100,000. This made Tabby's star one of the first big astronomy projects that was directly funded by the people. Through this, Boyajian and her team began continuous monitoring campaigns, using telescopes around the world to watch for new dips. The campaign also built a community of amateur astronomers and enthusiasts who felt invested in the mystery. For once, the study of a single star became a global group effort. The story by Boyajian shows that science doesn't always move forward with well-thought-out ideas, but with stubborn interest. She could have ignored the strange data or marked it as a mistake. She instead went after it. Tabby's star became a sign of science wonder because of how carefully she kept working on the case. Because she didn't brush off the strangeness, she gave us one of the most interesting cosmic puzzles of the 21st century. The crowd that found a mystery. As soon as Kepler started sending back its huge amount of data, it was clear that trained scientists would not be able to look it all through. It got so many light curves, each with a tiny flicker of brightness change, that study teams couldn't sort through them all in time. Computers could be taught to look for trends, but they missed the strange or thought that things that didn't fit the pattern were just noise. The people then stepped in. In 2010, the Planet Hunters project was born, part of the Zooniverse network of citizen science initiatives. The idea was bold but simple. Give ordinary people access to Kepler's light curves and ask them to spot dips that might indicate planets. Volunteers didn't need degrees in astrophysics. They just needed sharp eyes and patience. Human beings are remarkably good at spotting oddities in patterns, sometimes better than software. Over the next few years, thousands of volunteers worldwide scanned graphs of starlight. Most found small, regular dips, the telltale sign of planets orbiting their stars. But in 2011, a group of eagle-eyed participants stumbled across something that didn't fit. The light curve of a star labeled Tabby's star showed plunges of brightness so large and irregular that it looked like a mistake. The dips weren't neat or repeating. They were chaotic, as if a giant cosmic shadow had swept across the star at random. At first, many assumed it must be an error in the telescope data. After all, most light curves looked smooth, with clean planetary transits. But when more volunteers flagged the same bizarre graph, the anomaly became harder to ignore. Word spread across the Planet Hunters forums. The star was flagged again and again by different sets of eyes. These were not isolated misclicks. Something truly strange was hiding in plain sight. People with no formal training can make real contributions. In this case, it was volunteers, teachers, retirees, students, office workers, who first pulled Tabby's star out of obscurity. Their persistence forced the professional astronomers to take a closer look. Without them, the star might have been lost in the ocean of data, dismissed as a glitch or simply overlooked. Once the anomaly reached professional hands, Tabitha Boyajian and her colleagues took over, carefully analyzing the data and writing the formal paper. But the seed of the discovery was planted by everyday people clicking on graphs in their spare time. This collaboration highlights a profound truth about modern science. The universe is too big for any small group to explore alone. Sometimes, The most important eyes are not behind expensive telescopes, but on home computer screens. The volunteers didn't just spot the dips, they helped characterize them. On the Planet Hunters forums, discussions grew into heated debates. Some suggested comets, others guessed at dust clouds, while a few whispered about alien possibilities. While scientists remained cautious, the excitement among the public kept the mystery alive. By the time Boyajian's paper came out, there was already a global community invested in the fate of one star. The Planet Hunters model also showed the power of collective intelligence. Each volunteer might only classify a handful of stars, but together they generated millions of classifications. Outliers like Tabby's star stood out because so many different people pointed at it. It wasn't just a single sharp-eyed observer, but the collective weight of hundreds of watchers that elevated Tabby's star to the spotlight. This also changed how professional astronomers viewed their role. Instead of being the sole gatekeepers of discovery, they became partners with the public. The collaboration blurred the line between expert and amateur. In the process, it also gave astronomy a human face. People around the world could say, "I was part of finding the most mysterious star in the galaxy." That sense of ownership is powerful. It transforms science from a distant abstract pursuit into something personal. Tabby's star is still being studied, and the work of citizen scientists is still being felt. A lot of amateur astronomers are still pointing their telescopes at it and adding their findings to databases that pros use. Even though the finding phase is over, the star is still being watched, in part because of the same volunteer interest that brought it to the public's attention in the first place. What's particularly fascinating about this part of the story is that it shows that big findings don't always come from prestigious universities or funds of $1 billion. They can be made by a high school student clicking on a graph during lunch, or by an older engineer who is interested in a hobby. Tabby's star was a very strange needle in Kepler's database, which was like a large pile of space junk. Not only did it take modern technology to find, but also thousands of human eyes ready to look carefully, one curve at a time. A dip too deep. They know what to expect when they use the transit method to study stars. A planet in orbit around a star stops a very small amount of its light. It is easy to see that the dip will be small and stay that way. Take Earth as an example. From far away, it would dim the Sun by less than 1%. About 1% would be blocked by Jupiter, the largest planet in our solar system. People were shocked when Kepler said that Tabby's star sometimes lost 22% of its light. It was impossible for a planet to cause that much fading. To get an idea of how big it is, picture a house with all the lights on. If someone goes by a single window, the glow will dim a little, but only for a short time. Now picture half of the windows being blocked by something big and strange all at once, and then they are opened up again. That was the level of the drama going on around Tabby's star. This wasn't just one event. In 2011, Kepler recorded a series of small dips. They looked odd, but nothing that couldn't be explained by dust or debris. Then came the bombshell. In 2013, the star's light plunged by a staggering 22%. For comparison, a gas giant planet with massive rings might cause a dip of 2 or 3% at most. This dip was more than 7 times deeper than anything caused by a planet. Something unimaginably large had moved across the star. Astronomers tried to piece together the scale. To block that much light, the object, or collection of objects, would have to be roughly half the size of the star itself. That's not a planet. That's not even a rogue world with rings. It's something colossal. Worse, the dip wasn't clean or symmetrical like a planet's transit. It was messy, jagged, and lasted for days. Whatever was out there wasn't solid or singular. It seemed like a cloud, a swarm, or perhaps a fragmented structure. The riddle was made more difficult by the randomness. If it had been a planet, the dip would have happened again after one rotation. Astronomers watched for the next turn, but nothing happened. Months went by, then years. There were other smaller drops, but nothing as big as the huge 22% drop. It was like the universe had pulled off a one-time trick that it wouldn't do again. Some suggested comets. a massive swarm of icy bodies stretching over tens of thousands of kilometers could in theory create an irregular dimming event. But comets leave trails of gas and dust that glow in infrared light when heated by a star. Kepler and follow-up telescopes didn't see that glow. No infrared excess was detected. The comet hypothesis could not explain both the depth of the dip and the silence of the infrared. Others thought about planetary catastrophes. What if a massive planet had been shattered by tidal forces or collisions, and its remains were passing in front of the star? That would produce irregular dips, but the amount of debris required to block 22% of the star's light was extraordinary. It would mean dozens of Earth-sized fragments or trillions of tons of dust, all aligned just right to cross our line of sight. The odds were incredibly low. Then came the boldest suggestion. What if it wasn't natural at all? A dip of 22%, irregular and non-repeating, matched what you might expect if pieces of a giant megastructure were orbiting the star. Maybe solar collectors, maybe panels, maybe something beyond our imagination. Most astronomers dismissed the idea as unlikely, but the sheer scale of the dip kept the speculation alive. After all, nature didn't seem to have an easy answer either. The dip also raised questions about time. If such a massive dimming happened once in Kepler's 4-year mission, how often did it occur? Once a decade? Once a century? Was Kepler lucky enough to catch a rare event, or do these dips happen frequently but unpredictably? Without long-term data, no one could say. That uncertainty added fuel to the mystery, because astronomers couldn't simply wait and watch. The star wasn't following any schedule we could predict. The 22% plunge remains one of the strongest arguments that Tabby's star is unlike anything else. Variable stars exist, but their fluctuations are smoother and tied to internal processes. Dust clouds dim stars, but usually with detectable infrared signatures. Transiting planets cause dips, but never that deep. Tabby's star stood apart, a category of one. A huge number of studies were based on this one unusual event. Each theory had to answer a simple question. What can block a fifth of a star's light without leaving any other clear signs? We still don't know the answer, but that one deep dive made sure that Tabby's star would always be remembered in the history of astronomy. Without it, the star might have been just another dusty system that was forgotten. It turned into the most mysterious star in the galaxy because of it. It was clear from how deep that dip was that our assumptions are not always solid. Astronomers thought they knew all the different things stars could do for a long time. The rules were then changed by one remark. At that moment, Kepler reminded us of why it's important to explore. The world is full of surprises that are just ready to be found. Comet swarms or cosmic smoke? They had to start somewhere when they first saw Tabby's star's strange dips. Comets seemed like the most logical answer because comets are messy, unstable things that can break up into pieces that can send dust over very long distances. A big group of comets circling close to the star could send enough stuff into its path to make it dim in strange ways. It wasn't the most brilliant idea, but it made sense based on what we know about physics. Jason Wright, Tabitha Boyajian, and others explored the comet hypothesis seriously. Imagine a massive comet, or a whole series of them, breaking apart as they swung near the star. Each fragment would trail dust and ice, creating long tails that could obscure light. A swarm of dozens, even hundreds of comets, could in theory block 20% of the starlight. If they were large enough and aligned perfectly with our view, the strange dips might be explained without invoking aliens or unknown physics. At first, this idea seemed attractive because it accounted for the irregularity. Comets don't move in neat circles like planets. Their orbits are elongated, their timing uneven, and their fragments unpredictable. A star surrounded by comet debris would produce dips that were messy and inconsistent, just like what Kepler saw. But then came the problems. Comets, when heated by a star, release gas and dust. That dust absorbs light and re-radiates it in the infrared part of the spectrum. Telescopes sensitive to infrared like NASA's Spitzer Space Telescope should have picked up a glow around Tabby's star if comet dust was the culprit. Instead, Spitzer detected nothing unusual. The star's infrared output was normal. It wasn't surrounded by glowing dust. The comet model also required extreme numbers. For the dips Kepler recorded, you would need dozens of giant comets, each bigger than Halley's Comet, passing in front of the star within a short time span. Not just once, but multiple times. That kind of swarm is unprecedented in astronomy. Our own solar system, for all its comets, has never produced anything close. It wasn't impossible, but it seemed very unlikely. Other researchers suggested that maybe it wasn't comets orbiting the star, but clouds of dust drifting between us and Tabby's star. These clouds could be much closer to Earth, floating in the interstellar medium, the thin soup of particles that fills space. If a giant dust cloud happened to line up perfectly with our view, it could block starlight in irregular ways. This cosmic smoke idea explained why dips didn't repeat, and why they varied so much. After all, drifting dust doesn't care about orbital mechanics. Interstellar dust scatters light, and it tends to affect blue wavelengths more than red. When astronomers studied the dips in multiple colors, they did find that blue light dimmed more strongly, which suggested dust. But once again, the scale of the dimming was hard to match with known types of dust. You would need huge, dense patches, and they would need to move in just the right way. It felt like forcing a puzzle piece that almost fits but leaves gaps. Some combined versions came out. There could have been comet pieces close to the star, and dust clouds moving farther away, both of which adding to the chaos. It's possible that Tabby's star was just in a messy part of the galaxy, where many layers of junk were lined up in our line of sight. But every time scientists tried to make a good model, problems came up. The lack of an infrared glow was too strong of evidence against the comet theory, not because it was impossible, but because it was no longer thought to be true. The dust near the star should be glowing brightly, but Tabby's star was still. If comets were to blame, they would have to have a very low amount of dust, or the time would have to be so exact that it would be hard to believe. Still, the comet idea holds a place in the story because it showed how far scientists were willing to stretch existing knowledge before turning to exotic explanations. Rather than jump to aliens, researchers tried first to find an answer among familiar celestial objects. That instinct is science at its best, cautious, grounded, and unwilling to leap to extraordinary claims without exhausting the ordinary ones. Alien megastructure headlines. Strange things happened in October 2015 when science and news stories about aliens met, not just in rags or science fiction blogs, but also in big media and news sites. Tabby's star was the source, and the thought was thrilling. What if the strange drops in light weren't caused by comets, dust, or broken planets? What if they were proof that intelligent people built something? A few weeks ago, Tabby's star wasn't just a strange entry in a computer. It was the star that might hide a Dyson sphere. The spark for this frenzy came from Jason Wright, an astronomer at Penn State University. Wright didn't say Tabby's star was proof of aliens. Instead, he pointed out that if astronomers were ever going to detect alien megastructures, this was exactly the kind of light curve that might reveal them. Imagine an advanced civilization trying to capture their star's energy by surrounding it with enormous orbiting panels or swarms of collectors. Those structures would block starlight in irregular ways, producing dips that didn't repeat like planets do. Tabby's star fit that picture almost perfectly. The idea of a Dyson sphere, or more accurately, a Dyson swarm, has been around since the 1960s. Physicist Freeman Dyson speculated that a truly advanced species might need so much power that it would build gigantic structures to harvest the energy of its star. To outside observers, such structures would appear as strange dimming patterns in starlight and perhaps an excess of infrared radiation as the structures re-radiated waste heat. Science fiction ran with the idea, but astronomers also tucked it away as a thought experiment, a way to think about the limits of technology and the search for extraterrestrial intelligence. So when Tabby's star dimmed by 22%, irregularly and without repeating cycles, the connection was irresistible. Natural explanations looked shaky. An alien megastructure sounded outrageous but tantalizing. Journalists jumped on the story. "Alien megastructure," ran the headlines. TV anchors talked about it. The public latched onto the phrase. In a culture hungry for signs we're not alone, this star became the perfect candidate. For scientists, the attention was both thrilling and frustrating. On one hand, the public was suddenly captivated by an astronomical mystery. On the other, the focus on aliens risked overshadowing the careful scientific process. Tabitha Boyajian herself was cautious, reminding everyone that the most likely explanations were natural, even if they were unusual. But in the public imagination, the alien megastructure star had already taken root. The interest didn't stop with headlines. The SETI Institute pointed its radio telescopes at Tabby's star, scanning for signals. If aliens had built massive orbiting structures, perhaps they were also broadcasting, intentionally or not. For weeks, SETI searched across multiple frequencies. The result was silence. No signals, no beacons, nothing that suggested intelligent activity. The radio quiet didn't kill the idea, but it deflated it. A megastructure without any radio signature seemed unlikely, though not impossible. The findings with infrared light were another blow. If huge solar detectors were taking in energy from a star, they would glow in infrared light and give off heat. Spitzer and the Wide-Field Infrared Survey Explorer, on the other hand, looked at Tabby's star and didn't see any strange light. Infrared light from the star was normal. The Dyson sphere situation said there would be a strong excess of heat, so that didn't make sense. The hypothesis did more than spark wild headlines. It framed Tabby's star as a benchmark for how astronomers might one day detect alien engineering. Even if Tabby's star turned out to be dust, comets, or something mundane, the episode proved that real data could mimic the signatures of megastructures. In that sense, it was a kind of rehearsal for the future. If we do stumble on artificial structures one day, the signal might look a lot like this: irregular dips that defy simple natural models. The media attention also had effects that were not expected. It made people and resources want to learn more about the star. Crowdfunding projects got bigger. Time to look through telescopes was reserved. Tabby's star was just one strange star among many others. But after the news story about the alien megastructure, it was one of the most closely watched things in the sky. For the general public, the appeal was obvious. Astronomical discoveries are often remote, abstract, and technical. But here was something people could grasp instantly: a star blinking in strange, unnatural ways. The jump from weird dips to maybe aliens was short, even if scientists stressed caution. And for once, the mystery wasn't about microbes on Mars or signals buried in static. It was about something vast and awe-inspiring, the kind of vision science fiction had prepared us for. The SETI silence. SETI, the search for extraterrestrial intelligence, knew it had to move quickly when news spread about the chance of an alien megastructure around Tabby's star. For many years, SETI has been scanning the sky for radio waves or laser bursts that could mean the presence of intelligent civilizations. The work is mostly quiet and boring. They scan thousands of stars but don't find anything. But when Tabby's star became famous in 2015, it went straight to the top of SETI's list of places to look for life. The reasoning was simple. If an advanced civilization had indeed built orbiting structures around its star, it might also leave behind other signatures. One possibility was intentional signals, beams of radio or optical light sent out to announce their presence. Another was unintentional leakage, the technological equivalent of radio chatter or industrial hum that spills into space. Either way, SETI telescopes had a chance to catch something. The Allen Telescope Array in California was among the first to turn its dishes toward Tabby's star. Over several weeks, astronomers scanned across multiple radio frequencies, searching for narrowband signals that nature doesn't produce. Natural processes, like pulsars, quasars, or magnetic activity, create broad, messy signals. But a narrow, focused spike in a specific frequency could be a hallmark of technology. The search was methodical. covering frequencies from 1 to 10 gigahertz, often called the water hole, because it's considered a good band for interstellar communication. The result was silence. No spikes, no pulses, no repeating patterns, just the normal hiss of cosmic background noise. A few false alarms popped up, signals that at first looked interesting, but these were quickly traced back to satellites, Earth-based interference, or other mundane sources. In the end, the Allen Telescope Array found nothing unusual. A lot of other groups joined in. Deeper scans were done by the Green Bank Telescope in West Virginia, which is one of the most accurate radio telescopes in the world. It is possible for Green Bank to pick up signs from star systems that are so far away that they are as weak as the energy from a single home light bulb. In a loud signal, aliens should have been able to be heard by Green Bank. But once more, there was quiet. Optical SETI was also brought into the mix. Instead of radio, these searches look for short bursts of laser light. A powerful laser pulse, aimed deliberately, could outshine a star for a fraction of a second and act like a cosmic beacon, but Tabby's star gave no such flashes. In both the radio and optical windows, the sky was quiet. The silence didn't prove aliens weren't there. It only sets limits. SETI's scans could rule out powerful, continuous transmissions in the observed bands. But what if an advanced civilization wasn't broadcasting at all? What if it used frequencies SETI wasn't monitoring, or spread signals so faint and intermittent that even the best telescopes missed them? In that case, the silence meant nothing. It was simply absence of evidence, not evidence of absence. The results made people less excited about the megastructure theory. If there was a high-tech society in Tabby's star that was making Dyson swarms, why wouldn't we hear something? Even leaks that weren't meant to happen could have gone into space from such a big project. Since there was no sign of the dips, it was most likely due to natural events. The event was both good and bad for SETI. On the one hand, it was a chance to show that you were ready. SETI can quickly move some of the most powerful tools on Earth toward a target when a possible anomaly shows up. The quiet, on the other hand, showed how hard it is to find understanding. Because the world is so big, even if something seems fishy, it's not likely to be fake. But silence itself is informative. Each null result helps refine our understanding of what to look for and how to design future searches. The scans of Tabby's star proved that SETI could set strong upper limits. No powerful radio transmitters are operating there, at least not in the bands we checked. No giant laser beacons are blinking in our direction. Whatever is causing the dimming, it's not shouting across the cosmos. In the years since, SETI has used Tabby's star as a case study. It shows how anomalies can serve as practice runs. If a real alien megastructure exists somewhere, its signals might look a lot like this. Irregular dimming, strange light curves, odd behaviors that defy natural explanations. But as Tabby's star demonstrated, even the strangest stars may turn out to be natural in the end. Dust in the data. When scientists started to figure out what was going on with Tabby's star, one theory slowly started to make sense. Dust. Dust seems like a very normal thing to blame for something as strange as a 22% drop in brightness, at least at first look. But the more closely the experts looked, the more they thought that dust might be the best explanation for many of the things they saw. The key was hidden in the light's small parts. When light from a star passes through dust, the particles scatter and absorb it. Crucially, they don't do this evenly. Smaller grains scatter shorter wavelengths, blue light, more strongly than longer wavelengths like red. That's why our skies are blue. Sunlight passing through Earth's atmosphere gets scattered, with blue light redirected more than red. Astronomers call this wavelength dependence. If Tabby's star's dips were caused by dust, then the star should appear to dim more at blue wavelengths than at red. And that's exactly what astronomers found. Using ground-based telescopes equipped with filters to split starlight into colors, Boyajian's team monitored the dips after Kepler's mission ended. The dips weren't uniform. Blue light fell off more steeply than red. This fingerprint pointed directly to dust. A solid, opaque object like a planet or a megastructure would block all wavelengths equally, dimming the star by the same amount across the spectrum. Dust left its calling card, but dust alone doesn't solve the puzzle. The amount of dimming was still extraordinary. To block a fifth of a star's light, the dust clouds had to be huge and thick, or spread across wide regions of space. Where would so much dust come from? One idea was that it originated near the star itself, perhaps from a disrupted planet or a series of comet breakups. Another possibility was that the dust was interstellar, drifting between us and the star, like clouds on a cosmic horizon. Infrared readings made things harder to comprehend. If a star warms dust, it should glow in the infrared, sending back the heat it took in. Still, Spitzer and other telescopes did not find any extra glow. That meant the dust wasn't staying close to the star, where it would get hot. It could be farther away, cooler, and harder to find instead. It was annoying that there was no infrared, but it did narrow down the possibilities. If dust was the problem, it had to be cold, sparse, or very fine-grained. The long-term fading of the star also seemed to support dust. Historical photographic plates indicated that Tabby's star had dimmed by about 15% over the past century. Stars don't usually fade that much without undergoing dramatic internal changes. Dust drifting into our line of sight, however, could cause a gradual fade over decades, like smoke drifting across a spotlight. Though some later studies questioned the accuracy of the century-long dimming trend, the idea reinforced the case for dust. Not all astronomers were convinced. The dips weren't smooth or simple. Some were sharp, dropping suddenly and rebounding in just days. That implied that the dust wasn't evenly spread but clumpy, as if made of thick patches rather than a uniform veil. How could such clumps form and survive? Dust clouds usually disperse quickly under radiation pressure from a star. For them to persist, something must be replenishing them. That raised the possibility of ongoing processes, maybe a planet slowly evaporating, maybe collisions among icy bodies constantly producing new dust. The dust hypothesis also forced astronomers to think about scale. To obscure so much light without glowing in infrared, the dust particles had to be tiny, smaller than a micron in size. Such fine grains scatter light efficiently but are easily blown away by stellar winds. That meant any dust present must have been replenished on timescales of years or decades. In other words, something around Tabby's star could still be active, continuously shedding material into space. A lot of experts thought that the dust theory was a good one. Even though it didn't use strange science or technology from other worlds, it matched the wavelength-dependent dips. It gave a better explanation for the randomness than planets. It fit with the bigger picture of stars surrounded by junk, even though the size of this one was different. Boyajian often said that dust might not be as exciting as megastructures, but it was science doing what it does best, which is finding the easiest answer that fits the facts. The star that fades for a century. It was already strange that Tabby's star's brightness would drop for short periods of time, but then someone said the star might be going out for good, over decades or even centuries. The Harvard Photographic Plate Collection, which is one of the oldest science collections, gave me this idea. From the late 1800s through much of the 20th century, astronomers photographed the night sky on glass plates, cataloguing stars long before digital detectors existed. These plates, stored in vast libraries, captured the brightness of stars across generations. In the 2010 S, researchers began digitizing and analyzing them with new software. When they checked Tabby's star, they noticed something curious. Compared to its brightness in the early 1900s, the star seemed to have dimmed by about 15%. If true, this meant Tabby's star wasn't just blinking in sudden dips, it was undergoing a long-term fade. That was shocking. Stars like it, mid-aged F-type stars, are supposed to shine steadily for billions of years. A steady century-long decline simply didn't fit with normal stellar behavior. It was like finding out your supposedly reliable streetlight was slowly dimming every night, even though the bulb wasn't supposed to wear out for ages. The claim, first made by Bradley Schaefer in 2016, immediately stirred debate. If the star really had dimmed that much over a century, it implied something huge was blocking more and more light over time. One dramatic possibility was a growing swarm of dust or debris, slowly thickening. Another, more speculative, was that some enormous process, natural or artificial, was evolving around the star, reducing its output from our perspective. But those opposed said there were problems. It's hard to use photographic plates. Over time they break down, emulsions fade, and it's hard to calibrate them. Extreme care must be taken when comparing light across decades. Some said the alleged fading could be caused by old equipment, uneven exposure, or bias in the measurements. In the end, a 15% drop over 100 years is not very noticeable. It seemed real, but was it really real? To test the claim, astronomers turned to more modern archives. The American Association of Variable Star Observers, AAVSO, had collected decades of brightness records from amateur astronomers worldwide. While these records showed some scatter, they hinted at the possibility of a long-term trend. More importantly, recent space-based missions like Gaia and continued ground-based monitoring gave clearer, more precise measurements. These newer data suggested that, yes, Tabby's star had faded slightly in recent decades, though perhaps not as dramatically as the century-long plate analysis suggested. The argument is still not over, but the long-term fade idea changed the way people talk about it. The star can't just be a bunch of comets going by if it's getting dimmer over time. Comet groups could explain rapid drops, but not a slow drop that lasts for 100 years. Dust was once again a most likely possibility. A huge collection of tiny particles moving into our line of sight could slowly dim the star and cause dips in the light when clumps went through. One suggested that Tabby's star might be consuming material from its surroundings, producing clouds of debris that sometimes obscure it. Another proposed that it might be ejecting material, slowly surrounding itself with a veil. Some even speculated about a fading intrinsic luminosity, though that would require physics not well understood for stars of this type. People outside of science were also interested in the century-long drop. Piece by piece, if a huge building were being built, wouldn't it slowly dim a star? With each new piece, a little more light would be blocked. That could add up to 15% over 100 years. Even though there is no direct proof for this idea, the long-term dimming fed those who liked the idea of strange possibilities. But most scientists leaned back toward dust and debris, even if the details were messy. Dust can mimic both short-term dips and long-term trends. The challenge is to explain why so much of it exists and how it continues to replenish itself. Tabby's star is not a young star with leftover building blocks from planet formation. It should be a clean system. The fact that it isn't makes it exceptional. Color dips and hidden clues. The color of Tabby's star's dips, not their size, was one of the most important things that led to new research. When Kepler first found the sudden drops in brightness, he was only measuring the star's overall light. Kepler didn't see a difference between red, blue, or green bands when it came to light. But scientists found a key clue when they pointed color-filtered ground-based binoculars at Tabby's star. On different bands, the dips were not all the same. In physics, this matters a lot. If something solid and opaque, like a planet or a giant structure, passes in front of a star, it blocks all wavelengths equally. The light dims by the same percentage across the spectrum. But if the culprit is dust, the dimming is chromatic, meaning some colors fade more than others. Small particles scatter blue light more strongly, while larger ones may affect red or infrared differently. The pattern of dimming acts like a fingerprint, telling astronomers about the size and composition of whatever is blocking the light. When Tabby's star dipped again after its Kepler days, Boyajian's team and others were ready. They are observed in multiple wavelengths simultaneously. The results were clear. The dips were chromatic. Blue light was affected more than red. This immediately ruled out solid, opaque objects as the main cause. No planet, no artificial panel, no massive moon could explain the color dependence. Instead, it pointed directly to dust. But what kind of dust? That was the next question. Dust can range from large rocky grains to tiny submicron particles. The way light dims at different wavelengths reveals the size distribution. For Tabby's star, The evidence suggested that the blocking material was made of very small particles, so small they would be easily blown away by the star's radiation pressure. That raised another puzzle. If the particles couldn't last long near the star, then something had to be replenishing them constantly. Spectroscopy added more detail. By splitting starlight into its spectrum, astronomers could look for absorption lines caused by specific elements. During some of the dips, faint signatures of sodium and calcium appeared, suggesting the dust wasn't just random interstellar material, but contained traces of rocky or icy bodies. This hinted at ongoing processes in the star's system, perhaps comets evaporating, asteroids colliding, or even a disintegrating planet. Infrared telescopes didn't see any extra heat because of the color sensitivity. The dust specks might not be able to receive enough energy to glow brightly in infrared if they were very small. Instead, they would spread starlight without giving off much heat that could be seen. This was a clever way to explain why there wasn't any extra infrared light and why there were clear drops in visible light. The color data didn't fix everything, though. There were dips that were deeper and harsher than others. The emphasis on color changed from one event to the next. The chromatic signal was strong in some cases and weaker in others. This suggests that the particles were of different sizes, or that more than one process was at work. Tabby's star may not have just one story, but several that cross. In most cases, dust is the main character, but not always. This is where astronomy becomes detective work. Each dip is like a new clue in an ongoing case. The chromatic signature narrows the suspect list, but doesn't identify the culprit. For example, a swarm of comet fragments could produce dust of the right size. So could collisions among asteroids. So could a planet being slowly torn apart by the star's gravity. Each scenario produces slightly different dust chemistry and grain size distributions. Untangling them requires more dips, more spectra, and more careful comparisons. What made the color evidence so powerful is that it pushed the debate out of the realm of pure speculation. Before, astronomers argued between comets, megastructures, and cosmic dust with little hard data to separate them. Now, the star itself was providing measurable fingerprints. While it didn't give a final answer, it tilted the scales strongly toward dust. It also highlighted how important it is to observe in multiple wavelengths. A single brightness curve can mislead, but colors carry the hidden physics of the particles doing the blocking. For most people, color dips might not seem like a big deal when compared to alien megastructures. For experts, though, it was the big moment. It proved that careful looking at the same thing over and over again through different filters and binoculars could help solve even the most challenging riddles. Tabby's star was still strange and puzzling, but now it had left a trail of proof that it was caused by real physical processes, not just wild guesses. Ruins of shattered worlds? There are many theories about what Tabby's star is, but one of the most exciting is the idea that we are seeing the after-image of a planet being destroyed. Instead of dust floating around randomly or comets breaking apart, what if the star's strange dips are caused by the pieces of whole worlds that have been destroyed? This theory began with the sheer scale of the dimming. Blocking 20% of a star's light takes an enormous amount of material. A handful of comets cannot cut it. Even thousands of comets would struggle. But the breakup of a large rocky planet, something Mars-sized or larger, would produce an immense cloud of debris. Chunks of rock, mountains of dust, and fragments of all sizes could fan out into orbit, creating the kind of chaotic, irregular dips Kepler recorded. Astronomers have evidence from other systems that planets can and do get destroyed. Some stars have dusty disks that look like the remains of collisions. White dwarfs, stellar corpses, often show traces of heavy elements in their atmospheres, thought to come from shattered planets or asteroids falling in. In young systems, we've seen signs of catastrophic smash-ups between protoplanets. Violence is part of cosmic evolution, so the idea that Tabby's star might have eaten or torn apart one of its own worlds isn't far-fetched. The physics works like this. A planet on an unstable orbit might wander too close to the star. Tidal forces, Gravity pulling harder on one side than the other can rip it apart. This is called the Roche limit. Once inside that boundary, the planet stretches, fractures, and eventually breaks into pieces. Those pieces then spread out, forming streams of debris. Over time, the fragments grind down into dust, but before they disperse, they can block huge amounts of light. Another possibility is collision. If two large bodies smashed into each other near Tabby's star, the impact would fling debris everywhere. The resulting dust cloud could be enormous, easily explaining dips of 10 or 20%. The timing would be chaotic, since debris moves on different orbits, creating irregular shadows as clumps pass in front of the star. This model neatly explains why the dips don't repeat. Unlike planets, which orbit on predictable schedules, collision debris doesn't form neat patterns. Instead, it creates clouds that spread, clump, and fade. One month you might see small dips, another month a huge one. This matches the messy, inconsistent light curve Kepler captured. Of course, there are drawbacks. The first trouble is with light. A quake that destroys planets should make both dust and heat. The pieces should glow in the infrared as they warm up in the star's light. However, telescopes have not seen a large increase in infrared light around Tabby's star. The pieces of the world must be very small, very cool, or have been around for a very short time, so that we caught them just as they were spreading out. Second, the timing is suspicious. Planetary destruction on this scale is rare. Catching it in action around one star in 150,000 feels like cosmic luck. Why Tabby's star, and why now? Some argue that Kepler's massive dataset makes it inevitable we'd catch at least one rare event. Others remain skeptical, suggesting the odds are still too long. Despite these issues, the shattered planet theory remains compelling because it connects to things we know happen elsewhere. Astronomers have seen disintegrating planets orbiting other stars, slowly shedding material that creates irregular dips. One famous case is K-IC 12557548, where a tiny rocky world appears to be crumbling under stellar heat, trailing dust behind it like a comet. If small planets can disintegrate, why not larger ones? Tabby's star might simply be the extreme case. It's also possible that Tabby's star used to have a lot of planets that are now breaking down. Planets' paths can become unstable when they interact with each other's gravity, causing one to fall too close to the star. This kind of chaos can happen over billions of years. If we're lucky, or bad, we might be seeing the remains of a system that used to work well. The shattered world hypothesis resonates because it feels both tragic and epic. Imagine a thriving planet, perhaps with moons or even oceans, torn apart into dust and rubble, its pieces circling a star like a funeral shroud. To us, it's just irregular dips in brightness. To the cosmos, it might be the end of the world. Astronomers want to know if this model fits the data better than comet groups or dust clouds. It does explain some of the puzzle so far, but not all of it. The biggest problem is that there isn't any strong IR output. It is hard to hide that much stuff from instruments that are sensitive unless the stuff has already cooled down or spread out. The interstellar curtain. Lots of ideas are based on things that are moving close to Tabby's star. Another way of thinking looks to the space between us and the star. The star might not be the source of the puzzle after all. Instead, maybe something in the huge void between the stars, dust clouds moving across our line of sight without making a sound, is working like a cosmic curtain. Interstellar space isn't truly empty. It's filled with the interstellar medium, thin gas, plasma, and tiny grains of dust scattered across the galaxy. Most of the time, this material is so sparse it barely affects starlight, but in some regions it collects into denser clouds, enough to dim or redden the light that passes through. Astronomers see this often in star-forming regions, where dust obscures newborn stars behind glowing nebulae. Could Tabby's star simply be unlucky, with an interstellar curtain drifting across it? This explanation immediately helps with one puzzle: irregular dips. Unlike planets or orbiting debris, which follow predictable orbits, interstellar clouds move along complex paths, pushed by galactic winds and magnetic fields. A clump of dust hundreds of trillions of kilometers away could easily slide between us and Tabby's star, dimming its light in chaotic ways. Such clouds could be patchy, with dense knots and thin regions, creating exactly the kind of sharp, uneven dips Kepler recorded. It also helps with the century-long fading. If a large dust cloud were drifting gradually across our line of sight, it could cause a slow, steady decline in brightness over decades. Like smoke drifting across a lighthouse beam, the light would fade not because the bulb changed, but because the curtain thickened. But there are concerns currently as well. There are certain visual features of interstellar dust. Starlight turns reddish because of it, and blue light is scattered more than red light. This color pattern can be seen in some of Tabby's star's dips, but it doesn't always match the pattern of normal cosmic dust. We wouldn't expect the dips to be as sharp and dramatic if they were from a curtain very far away. Another issue is scale. For interstellar dust to block 20% of a star's light, the cloud would need to be unusually dense. Such dense clouds are not unheard of, but they are rare and usually obvious, showing up as dark patches against the Milky Way. Yet Tabby's star isn't located behind any known dense nebula. Its region of the sky looks clear. That makes the interstellar curtain idea harder to support. Astronomers tested the hypothesis by looking at nearby stars. If the dimming were caused by dust between us and Tabby's star, then other stars in the same region of the sky, lying just behind the same cloud, should also dim in similar ways. But when researchers checked, they didn't find the same bizarre dips in neighboring stars. This suggested that whatever was blocking the light was unique to Tabby's star, not a shared foreground veil. There are, however, subtler options. Some experts think that too small or too faint strands of dust might be floating around in space and not being able to be seen. From our point of view, these strands might line up perfectly with Tabby's star. But they might miss close stars by a small enough amount that we wouldn't notice. There are a lot of small bumps in space, and it's possible that we're stuck looking through one of them. There's also the idea of circumstellar-interstellar interaction. Tabby's star might be shedding material like gas or dust, which then mixes with the interstellar medium nearby. The result could be a hybrid curtain. Not entirely interstellar, not entirely circumstellar, but something in between. This would explain why the dips sometimes behave like dust close to the star and other times like dust farther out. Even though the interstellar curtain theory doesn't fit perfectly, it hasn't been ruled out. It remains one of the more natural, grounded possibilities. If true, it would mean Tabby's star is ordinary after all, and the mystery lies in the thin, drifting dust clouds between us. It wouldn't be the first time cosmic dust has fooled astronomers into overestimating a mystery. Still, a lot of experts aren't sure if they fully agree with this explanation. It's not a good candidate because the dips are too sharp and there aren't any similar effects in stars nearby. Most likely, the truth is a mix of things: dust close to the star, possibly from comets or broken planets, plus tiny inputs from space along the way. Like layers of curtains overlapping, each one changes the light in its own way, which is what makes the flickers we see. Mining the sky. When a cosmic paradox won't accept common answers, people start to think about strange things. One of the craziest but most interesting ideas about Tabby's star is that the dimming might be a result of business going on outside of Earth. It's possible that what we're seeing is not planets, comets, or dust clouds, but signs of large-scale mining activities going on around the star. The idea comes from the scale and irregularity of the dips. A 20% plunge in brightness suggests something enormous crossing the star's face, but the dips don't repeat in tidy cycles like a planet's orbit. Instead, they look messy and chaotic, as if clouds of material are being moved around, rearranged, or even consumed. To some, that randomness looks less like nature and more like activity. The mining hypothesis imagines an advanced civilization dismantling comets, asteroids, or even planets near Tabby's star to harvest raw materials. A growing society might need metals, silicon, and volatiles on a scale that dwarfs anything humanity could dream of. To fuel energy demands, they might strip whole planets for resources, launching enormous clouds of dust and debris into space. From our distant vantage point, those operations could look like irregular dips in brightness, just like Kepler saw. This idea has been played with in science fiction for a long time. Arthur C. Clarke wrote about societies that gather stars for food. People today think about Kardashev Type 2 societies, which make the most of all the energy and materials they have. At that level, mining a star system would create huge debris fields, teams of collectors, and maybe even temporary buildings. These are the same kinds of irregular shadows that Tabby's star casts. But how could astronomers even test such a wild idea? They start by asking, if a civilization were mining a system, what signatures would it leave behind? One possibility is unusual dust chemistry. Mining and processing planetary material might produce dust clouds rich in metals or exotic compounds. Spectroscopy could, in theory, pick up hints of these elements in the star's light. To date, no clear evidence of industrial chemistry has been found around Tabby's star. But the sensitivity of our instruments limits what we can detect. Waste heat is another thing that could be a sign. A lot of industrial processes lose energy, which is released as infrared heat. But, just like with the Dyson sphere idea, telescopes like Spitzer didn't find any extra infrared light coming from Tabby's star. If there is industry there, it would have to be very good at hiding waste heat, or work on much smaller scales than was first thought. Critics argue that the mining idea is a last resort, pulled in only because other explanations are unsatisfying. And that's true. There's no direct evidence of industry at Tabby's star. Dust, comets, and shattered planets all remain better supported by data. But the appeal of the mining theory is that it takes the irregularity seriously. Where natural models stumble, speculation about purposeful activity fills the gap. Still, it's worth remembering that speculation has value in science. Even if it turns out Tabby's star is natural, asking what if it's not helps researchers refine their methods. It forces us to think about what real alien engineering would look like and how we'd tell it apart from dust. If advanced civilizations do exist, their activities might mimic natural astrophysics. By studying Tabby's star, scientists sharpen the tools needed to recognize the difference. Some experts don't take the mining theory at face value. Instead, they see it as an exercise in thought. Tabby's star might look a lot like the light curve if people took planets around a star apart. That is useful information. It gives us a starting point. These are the kinds of oddities we should notice. Even if the real answer is dust, Tabby's star gives us a look at what alien business might look like. Crowdfunding a cosmic mystery. After everyone found out about Tabby's star, scientists were let down by the fact that the Kepler Space Telescope had moved on to other things. That star was no longer in its field of view, and without new information from space, the puzzle might become less important. Big sites on Earth might be able to help, but time on those telescopes is very expensive and in high demand. Most of the time, scientists have to ask for time to observe months in advance, weighing the benefits of each hour against hundreds of other projects. It might not seem important to study a star with weird dips when compared to projects like mapping galaxies or looking for worlds where people could live. That's when Tabitha Boyajian and her colleagues did something unusual. They turned to the public. In 2016, Boyajian launched a Kickstarter campaign called The Most Mysterious Star in the Galaxy. The goal was simple: raise money to fund dedicated ground-based observations of Tabby's star, so astronomers could keep watching for new dips in real time. If another big dimming event occurred, they wanted to be ready with multiple telescopes, not scrambling after the fact. The response was overwhelming. Thousands of people from around the world donated, many of them ordinary enthusiasts who had followed the star's story in the news. In total, the campaign raised over $100,000, enough to secure ongoing observations from a network of telescopes. This was more than just money. It was a signal that the public cared deeply about this star and its mystery, enough to personally bankroll the science. The fund supported the Las Cumbres Observatory Global Telescope Network, a unique system of robotic telescopes spread across the globe. With instruments in both hemispheres, they could keep a near-continuous watch on Tabby's star day and night. For the first time, astronomers weren't relying on luck to catch the dips. They had the tools to monitor the star systematically, ready to capture its flickers in detail. This approach paid off almost immediately. In 2017, the star dipped again, and thanks to the new monitoring campaign, astronomers caught it live. Multiple telescopes observed the dimming in different wavelengths, confirming the color dependence that pointed to dust. Without the crowdfunding, this crucial evidence might have been missed. It was a triumph not just for the scientists, but for the thousands of donors who had made it possible. The crowdfunding campaign also created a new kind of relationship between scientists and the public. Traditionally, science operates at a distance. Researchers publish papers, journalists report on them, and the public reads about discoveries long after the fact. But here, people felt like participants. Backers weren't just donating money, they were joining a team. Updates were sent out as dips happened, and ordinary people felt the thrill of discovery alongside professionals. The mystery of Tabby's star became a shared adventure. It also showed how astronomy is adapting to the 21st century. In an era where social media amplifies every story and where people crave involvement, science can thrive by being open and inclusive. Tabby's star demonstrated that if you give people a mystery and invite them into the process, they will respond with enthusiasm. For a field often strapped for funding, this was a lesson in creativity and community. Critics have pointed out that crowdfunding can't take the place of more usual ways of getting money. Not every star will be famous all over the world, and not every project will get people to donate, but it was very helpful in rare cases like Tabby's star. It also gave scientists more freedom. They didn't have to wait for permission from the government to act. Instead, they could move quickly because the people supported them. The ad also talked about how science can make people feel. Donors weren't giving money because they knew a lot about light curves or F-type stars. They gave money because they were amazed. One star, 1,500 light-years away, was flashing in a way that no one could explain. Finally, they could help figure out what was going on. It wasn't science as a dry study, but as a story that was coming to life. Tess joins the hunt. A lot of people were afraid that the story of Tabby's star would lose steam after the Kepler Space Telescope's mission was over. After all, Kepler was the one who saw the sudden drop in light of 22% that made this star famous. However, TESS, the Transiting Exoplanet Survey satellite, was ready to take over just as Kepler's work was coming to an end. Launched in 2018, TESS was designed to be Kepler's successor, but with a different approach. Instead of staring at a single patch of sky for years, TESS surveys nearly the entire sky, sector by sector, building a huge catalogue of exoplanets. Its wide-field cameras can monitor thousands of stars at once with incredible precision. For Tabby's star, that meant a new opportunity. If the star flickered again, TESS might catch it in action. From the start, astronomers hoped TESS would provide fresh clues. Its instruments are sensitive to small brightness changes, just like Kepler's, though with slightly different precision and cadence. More importantly, TESS offered the chance to see if the strange dips continued in the years after Kepler. If the star's behavior had been a one-off event, then perhaps the mystery would fade. But if TESS observed new dips, it would confirm that the star remained unpredictable. The first TESS observations of Tabby's star showed that the star was still flickering, though the dips appeared shallower than the dramatic ones Kepler had caught. Instead of plunges of 20%, the dimmings were closer to 1 or 2%. These smaller dips were easier to explain with dust, but they confirmed that the system was still active. Tabby's star had not settled down. Whatever process was driving the irregular behavior was ongoing. TESS also brought a new advantage: coordination. Because its observing schedule is public and predictable, astronomers on the ground could prepare to monitor Tabby's star at the same time. This allowed for simultaneous observations in multiple wavelengths. When TESS saw a dip, ground-based telescopes could immediately check the color dependence, looking for dust signatures. This combination of space-based and Earth-based monitoring turned the mystery into a global effort. Another benefit of TESS was context. By surveying such a wide swath of the sky, TESS could identify other stars with unusual dips. If Tabby's star was truly unique, it would stand out as a solitary case. But if TESS found cousins, other stars with irregular dimmings, it might suggest a new class of stellar behavior. And indeed, TESS has revealed several candidates with odd light curves, though none as extreme as Tabby's star. This comparative data helps researchers understand whether Tabby's star is an outlier or part of a broader phenomenon. The smaller dips observed by TESS strengthened the dust hypothesis. Their wavelength dependence matched what you'd expect from tiny grains scattering light. Combined with data from the Las Cumbres Observatory network, the evidence tilted heavily toward dust clouds rather than planets or megastructures. Still, the irregular timing and the persistence of the phenomenon left room for debate. When it came to science, TESS wasn't as exciting as Kepler had been. It did not manage to avoid a huge 20% drop. But the fact that it was constantly and well watched was just as important. For continuity's sake, it kept the puzzle living in the data instead of letting it drift into guesswork. Tabby's star wasn't just a one-time surprise from Kepler. TESS kept an eye on it, and it continued to be a puzzle. The people knew that the puzzle was still being solved when TESS got involved. After the initial alien megastructure craze, the media's interest had lessened, but TESS opened up new ways to keep the story going. Not because it proved aliens, but because it showed that the star was still doing something strange. Each new dip made the news. There was still a secret. In many ways, TESS normalized Tabby's star. By placing it within the broader landscape of stars with odd light curves, TESS reminded astronomers that nature is more varied than we often expect. Kepler found the first shocking clues, but TESS gave perspective. Strange behavior may not be unique, just rare. And studying these rare cases could reveal processes we don't yet fully understand: collisions, dust production, or even subtle stellar instabilities. Gaia's precision map. To solve difficulties about stars, it's just as important to know where they are and how they move as it is to watch them change. That's where Gaia from the European Space Agency comes in. Gaia, which was launched in 2013, is making the most accurate 3D map of the Milky Way ever by recording where more than 1 billion stars are, how they move, and how far away they are from each other. Gaia's data gave Tabby's star something very useful: background. First, distance. Before Gaia, the distance to Tabby's star was estimated with moderate uncertainty. Early estimates placed it around 1,480 light-years away. Gaia refined that measurement with parallax, the tiny wobble of a star's position against the background as Earth orbits the Sun. Gaia pinned the distance to about 1,470 light-years with far smaller error margins. Why does this matter? Because distance affects brightness. If the star is closer than we thought, it might actually be dimmer intrinsically; if farther, brighter. Knowing the true distance lets astronomers calculate the star's real luminosity, which in turn helps test models of what could be blocking its light. Second, motion. Gaia measures proper motion, the star's drift across the sky relative to background objects, and radial velocity, its motion toward or away from us. Tabby's star turned out to be a fairly ordinary F-type star, moving in line with expectations for stars in its part of the galaxy. No strange accelerations, no odd companions tugging it off course. This ruled out some exotic scenarios, such as the possibility that a hidden stellar companion or nearby object was interfering with the light curve. Third, stellar classification. Gaia's precise photometry confirmed that Tabby's star really is an F-type main sequence star, about 40% larger and hotter than the Sun. This was important because some skeptics wondered if perhaps the star had been misclassified. If it were a different type, say a variable giant, it might naturally fluctuate. But Gaia's data reinforced the original view. Tabby's star is not a variable giant. It should be stable. Its erratic dips are not normal for a star of its class. Gaia also gave a bigger picture of the world. Astronomers were able to get a better idea of how much dust is in the space between us and Tabby's star by making a picture of where the dust is in the Milky Way. The results only showed some cosmic dust in the line of sight, which is not nearly enough to explain the deepest dips. This made the interstellar curtain theory less strong and pointed back to dust around the stars or in the area as the main cause. Gaia's collection made it possible for scientists to compare Tabby's star to thousands of other stars that had qualities that were similar to its. This data background is important. Tabby's star wouldn't be the only F-type star with strange dimming if many of them did, but Gaia acknowledged that it was rare. There are billions of stars being watched, and only a few show light curves that are even close to this one. Tabby's star was still unique. It wasn't part of a bigger group. One subtle clue from Gaia involved stellar companions. The mission is sensitive enough to detect wobbles caused by hidden binary partners. Tabby's star does have a faint red dwarf companion about 900 astronomical units away. A huge separation, more than 20 times the distance between the Sun and Pluto. While too far to directly cause the dips, this companion could play a role indirectly, perhaps perturbing comet reservoirs or distant debris belts, sending material inward toward the star. This gave some weight to the comet and debris models, which need a trigger to replenish dust. Gaia also measured the star's stability over time with exquisite precision. Unlike variable stars, which show rhythmic changes in brightness, Tabby's star does not pulsate. Its underlying luminosity is stable, confirming that the dips come from external material rather than the star itself, flickering intrinsically. This helped close the door on some theories that suggested internal stellar changes. Gaia didn't solve the problems, but it did make the rules stricter. That number told us how far away the star is, how bright it is, how it moves, and what kind of star it is. It ruled out mistakes in classification, ruled out simple dust accounts for what was happening in the foreground, and pointed at possible roles for partners far away. The most important thing it did was tell science that Tabby's star is not like other stars. Gaia has measured 1 billion stars, and almost none of them act in this way. Infrared silence. Tabby's star is particularly strange because of what can't be seen when it gets dim. If big clouds of dust or other junk are covering the star, they should get hotter as they take in its light. After that, that heat would be sent back out as infrared energy, glowing slightly but clearly to devices that can pick it up. But scientists who used infrared light to look at Tabby's star found nothing. This was first tested with NASA's Spitzer Space Telescope and the Wide Field Infrared Survey Explorer, WISE. Both are designed to detect heat signatures that human eyes can't see. They've revealed warm disks around young stars, dusty shells around dying stars, and even the faint glow of brown dwarfs. But in the case of Tabby's star, these observatories reported no unusual infrared excess. Its infrared output was almost exactly what you'd expect for a normal F-type star. No hot dust, no giant debris belt, no warm clouds glowing after blocking starlight. This absence is often called the infrared silence. It's one of the strongest pieces of evidence against many popular theories. If the dips were caused by comets or planetary collisions, the resulting dust should radiate strongly in infrared. If the dips were caused by an alien megastructure, its waste heat would leak into the infrared as well. A Dyson swarm collecting 20% of a star's light would shine brighter in infrared than the star itself. The silence made both natural and exotic explanations harder to support. But scientists didn't give up. Instead, they asked, what kind of dust could block visible light without glowing much in the infrared? The answer lies in size. Very small dust grains, less than a micron across, can scatter light effectively while absorbing very little. They can cause noticeable dimming in visible wavelengths, but produce minimal heat signatures. This fits with the color-dependent dips seen in ground-based telescopes. The problem is, such fine dust doesn't last long near a star. Radiation pressure pushes it away quickly, meaning something has to keep replenishing it. The dust might not even be close to the star, which is another option. If it is farther away and in a colder part of space, it might never get hot enough to give off a strong infrared glow. This would explain why there isn't any extra infrared light, but dust could still block light. But that brings up another question. What could throw so much matter into the outer system, and why does it look like it's all clumped together when we look at it? The infrared silence also pressured the planetary collision hypothesis. When planets smash together, they produce immense amounts of hot debris. We've seen this around other stars, warm disks glowing brightly in infrared, lasting for millions of years. Tabby's star shows no such glow. If a collision happened, it must have been either much farther in the past, with the dust now cooled and dispersed, or somehow involved unusual conditions that suppress the infrared output. Neither explanation is particularly satisfying. The alien megastructure idea was hit hardest by the infrared silence. A Dyson swarm is essentially a gigantic solar collector. Even if aliens were extraordinarily efficient, no technology can use energy without wasting heat. That heat has to go somewhere, and physics dictates it would radiate in infrared. The fact that Spitzer saw no excess was a near-death blow to the megastructure hypothesis. Unless the civilization had technology to dispose of heat in some unknown way, something beyond known physics, the lack of infrared emission ruled it out. Even with these changes, the silence is still helpful. Things that aren't there can be just as important as things that are. Astronomers could rule out whole groups of theories if they couldn't find infrared. So only situations involving cold, fine dust, or other strange processes were left in the running. Models had to change over time, getting smarter and more limited by real findings instead of just guesses. Infrared silence also highlighted the importance of multi-wavelength astronomy. Kepler's visible light data was only the beginning. Spitzer, WISE, and other instruments expanded the picture by looking at different parts of the spectrum. Together, they built a fuller story. Tabby's star dims in visible light, but not in infrared. That contrast is a clue in itself. Not alone, other weird stars. At first, Tabby's star seemed like a strange, one-of-a-kind thing. It had a strange light curve that looked like nothing else in astronomy. It dropped by 20% and didn't repeat itself. As more information came in from Kepler, TESS, and studies done on the ground, scientists realized that Tabby's star might not be going it alone. Even though they weren't as strong, other stars also dimmed in ways that couldn't be explained easily. One example is RZ Piscium, a star about 550 light-years away. Often nicknamed the evil twin of the Sun, it has been observed dimming erratically by as much as 10%. Spectroscopic data suggests the dips are caused by dusty debris, possibly from a planet or asteroid being destroyed. In some ways, RZ Piscium looks like a younger cousin of Tabby's star, a system where planetary chaos is producing clouds of material that block light in unpredictable bursts. Another case is the star kick 125575548, also observed by Kepler. This star shows repeating dips of about 1%, but with a twist. The dips vary in depth from orbit to orbit. Astronomers think this is due to a small rocky planet literally disintegrating as it orbits too close to the star. Each pass sheds dust, creating a changing comet-like tail that blocks varying amounts of light. While smaller in scale, it demonstrates that stars can host unstable systems that mimic some of Tabby's star's strangeness. Then there's EPIC 204278916, another young star studied during Kepler's K2 mission. It exhibited a dramatic 30-day dimming event, with brightness dropping by 65%. This was even deeper than anything seen at Tabby's star. Astronomers think the culprit may have been a warped, dusty disk seen edge-on. While Tabby's star is not young and shouldn't have such a disk, EPIC 204278916 proves that extraordinary dimmings can occur in other contexts. These examples matter because they provide comparison points. If Tabby's star were truly unique, its mystery might demand exotic explanations. But the fact that other stars also show irregular dips, sometimes from debris, sometimes from disks, sometimes from disintegrating planets, suggests that extreme dimming may be part of a broader family of phenomena. Tabby's star is simply the most dramatic and puzzling member of that family. Large-scale surveys have also helped. Projects like ASAS-SN, All-Sky Automated Survey for Supernovae, and ZTF, Zwicky Transient Facility, monitor millions of stars for variability. Among them, astronomers have identified a handful that show Tabby-like behavior, irregular dips not easily explained by transiting planets. None are as famous or as well studied, but their existence keeps the debate grounded. Tabby's star isn't a cosmic outlier carved from a different set of rules. It's part of a spectrum of strange stellar behavior we're only beginning to catalogue. At the same time, Tabby's star remains distinctive. Its century-long fade, the combination of shallow flickers and deep plunges, and the absence of infrared excess make it stand out. Other stars may flicker, but none tick all the same boxes. This uniqueness is what makes it so stubbornly mysterious. Still, the growing list of weird dimmers gives hope that patterns will eventually emerge. If we can explain the cousins, maybe we can explain the star that started it all. A unique aspect about these stars is that some of them are young, while Tabby's star is older. This shows that more than one process may be at work. In new systems, rings and debris from planet formation naturally cause dips that aren't straight. In older systems like Tabby's star, the same dips could be caused by planets being destroyed or dust clouds coming back to life. Astronomers can test which theories work in different situations by analyzing stars of different ages and types. The discovery of other weird stars also shows the power of modern astronomy. Before Kepler and TESS, many of these anomalies would have gone unnoticed. Stars flicker all the time from Earth's perspective, but without precise, continuous monitoring, small or irregular dips get lost in the noise. Space telescopes changed that, revealing that the universe is more chaotic and unpredictable than our neat textbook diagrams suggest. JWST's future role. When the James Webb Space Telescope launched in December 2021, astronomers celebrated the arrival of a new era. With its massive 6.5-meter mirror and instruments tuned to infrared wavelengths, JWST was designed to peer deeper into the cosmos than ever before. Galaxies, exoplanet atmospheres, star formation, all of these are within its grasp. But for those fascinated by Tabby's star, JWST represents something else. The best chance yet to pry open the mystery of the galaxy's strangest dimmer. Infrared is where JWST shines, and infrared is exactly where Tabby's star has been silent. Previous telescopes like Spitzer and WISE detected no excess heat, no glow from warm dust, but their sensitivity was limited. JWST can see fainter signals, distinguish finer details, and separate overlapping sources with higher precision. If there is even a whisper of infrared excess around Tabby's star, JWST should be able to detect it. Finding that glow would confirm that dust really is the culprit, while failing to find it would make the puzzle even sharper. JWST also offers spectroscopy with unprecedented clarity. By splitting the star's light into its component wavelengths, astronomers can search for the signatures of specific molecules or minerals in any dust clouds. Sodium, calcium, silicates, even organic compounds leave telltale absorption features. Previous ground-based spectroscopy hinted at some of these elements during dips, but JWST's instruments could provide definitive confirmation. Knowing exactly what the dust is made of could reveal whether it comes from evaporating comets, colliding asteroids, or even the remains of shattered planets. Time is another perk. It's hard to study because Tabby's star doesn't dip at set times, but JWST's adaptable viewing modes and ability to work with ground-based cameras could make it possible to quickly check back if a dip starts. Once the star starts to fade, JWST can use images and spectra to get a very close look at the event. Astronomers would have the best picture yet of what's passing in front of the star if they could watch a dip happen in real time and across many bands. JWST also has the potential to test more speculative ideas. For example, if the dips were caused by artificial structures, their spectral signatures might look different from dust. Smooth, Wavelength-independent blocking would suggest solid panels or large opaque bodies, while chromatic dependence would suggest dust. JWST could push these distinctions further than ever before, probing subtle differences in how the light dims. Even beyond direct observations, JWST's role in studying Tabby's star fits into a broader program. By examining other stars with strange dimming events, JWST can help place Tabby's star in context. If multiple systems show faint infrared signatures, astronomers can compare them, identifying common mechanisms. If Tabby's star continues to stand alone, its uniqueness will become even more significant. Either way, JWST will sharpen the boundaries of the mystery. There's also the chance of coincidence. Astronomers have already been surprised by what JWST has found in its first few years. Galaxies that are older than expected, huge storms involving exoplanets, and worlds far away with complex chemistry. The findings of Tabby's star might also be surprising. A strange spectral feature, a faint glow at the right wavelength, or a quick deep dip during a time for observation could change the argument overnight. But one of JWST's greatest strengths is precision. Its ability to measure small changes in light and color with high accuracy means that even modest dips at Tabby's star could reveal layers of detail we've never seen. Tiny differences in grain size, composition, or distribution become measurable. Instead of broad guesses about dust, astronomers could speak in specifics, silicate grains of a particular size, or gas molecules consistent with evaporating ice. Of course, JWST time is valuable. There are thousands of scientists from all over the world who want to be on its schedule, but only the best ideas are chosen. Galaxies on the edge of time and exoplanets in livable zones are what Tabby's star has to deal with, but the fact that it is one of the weirdest stars known to science makes its case strong. A lot of the time, understanding strange things is what leads to big discoveries. JWST was designed to take on just that kind of task. The human fascination with mystery. A lot of people were interested in Tabby's star when it first hit the news, not just experts. The story was quickly picked up by news sites, blogs, YouTubers, and regular people who read for fun. Why? Because the flashing light of a faraway star touches on something very human: our desire to know more about the world around us. People are wired to notice patterns. We see faces in clouds, animals in constellations, and meaning in random noise. When a star dims in a way no one can explain, our brains light up. We want to solve the puzzle, to connect the dots, even if the answer isn't clear. The fact that Tabby's star's dips defy prediction only intensifies the effect. The irregularity teases us, like a riddle missing its last line. Mysteries like this also spark imagination. Scientists propose dust, comets, or shattered planets. But the public leaps further, asking, what if it's something artificial? What if we're glimpsing signs of life beyond Earth? Even though the evidence for aliens is thin, the mere possibility resonates. The idea that we could detect another civilization, not by hearing their voices, but by watching their shadows, feels like science fiction come to life. This fascination isn't new. History is full of cosmic mysteries that grip the public. In the 1800s, astronomers mistook canals on Mars for signs of intelligent life. In the 20th century, pulsars were jokingly nicknamed LGM, Little Green Men, before scientists realized they were neutron stars. Each time, the excitement wasn't just about the discovery itself, but about what it might mean. Tabby's star is the modern heir to this tradition, a cosmic riddle that makes us wonder if we're not alone. But fascination goes beyond aliens. Even the natural explanations, dust clouds, planetary debris, interstellar curtains, capture attention because they reveal the violence and beauty of the universe. People are drawn to the drama of shattered worlds and the elegance of dust scattering light. A mystery like Tabby's star offers both the thrill of the unknown and the awe of cosmic processes bigger than ourselves. Psychologists point out that uncertainty is one of the strongest drivers of curiosity. When something doesn't fit our expectations, it nags at us. We can't let it go. Tabby's star refuses to fit. and so it refuses to leave our minds. Unlike a solved puzzle, which we set aside, an unsolved one keeps pulling us back. Each new observation, each paper, each theory feels like a potential key that might finally unlock the door. There's also a communal aspect. Mysteries invite conversation. People share theories online, debate possibilities, and speculate together. Tabby's star created a global discussion that spanned professional circles and kitchen tables. It blurred the line between experts and amateurs, making everyone feel like they could contribute. That sense of shared wonder is powerful. It transforms a single star into a story the whole world can follow. The way experts talk about logic makes it even more thrilling. Many experts didn't hide behind language. Instead, they were honest about how confused they were. The star was called the most mysterious object we've ever found by Tabitha Boyajian herself. People pay attention when experts say they are confused. It makes the puzzle more interesting and real. Of course, fascination has a downside. Headlines about alien megastructures spread faster than cautious explanations about dust. People love the extraordinary more than the mundane. When dust became the leading theory, some lost interest, feeling disappointed. But in truth, dust itself is extraordinary. The fact that grains smaller than a micron, drifting in space, can trick an entire planet's worth of scientists is remarkable. The psychology of aliens. When the news about Tabby's star came out, one word stood out: alien megastructure. Scientists had mentioned it as a faint chance, but people were excited about it right away. There was no technical reason why the idea spread faster than the idea itself. Why? Because our minds are set up to think that when something strange happens, someone must be on the other end of it. This instinct has deep roots. On Earth, survival often depended on spotting patterns. A rustle in the grass might be the wind, but it might also be a predator. Our brains evolved to assume intention, because it was safer to see agency where there was none than to miss a real threat. That same bias carries over into how we interpret the cosmos. A star flickering unpredictably? Our first thought is, who is doing that? That's why aliens dominate public imagination whenever astronomy throws up an anomaly. From canals on Mars to radio signals like the famous WOW detection in 1977, people lean toward explanations that involve intelligence. It's not just curiosity, it's the hope that we're not alone. Tabby's star tapped directly into this longing, offering a stage where our deepest psychological drives could play out. For scientists, the psychology of aliens is a double-edged sword. On one hand, it fuels excitement and public interest. Crowdfunding campaigns succeed, telescopes get time, and students sign up for astronomy classes because they're drawn to mysteries with alien potential. On the other hand, fascination can overshadow real progress. When headlines scream about megastructures, subtle but important discoveries about dust scattering or stellar behavior get ignored. The alien hypothesis also reveals how humans think about scale. We can imagine comets and dust clouds, but they feel small and unsatisfying compared to a civilization building structures bigger than planets. Our minds crave grandeur, and the alien explanation scratches that itch. It elevates the mystery into something worthy of myth. Dust is science, aliens are legend. It's remarkable that this attitude can affect even experts. While most people stay careful, a lot of them quietly say that the thought of aliens is always in the back of their minds when they think about things that don't make sense. They don't think it's the answer, but they understand why people are drawn to it. Tabby's star was the right subject because it was a star that was too normal to act this weird, dipping in ways that didn't fit any natural model. It looked like this place was going to give away how smart it was. Belief in aliens isn't just about curiosity, it's about meaning. The universe is vast, and for many people, the thought that we're alone feels intolerable. When Tabby's star flickered, it seemed to whisper, "Maybe you're not." That whisper resonates far beyond the data. It touches philosophy, religion, and culture. Even when scientists ruled out megastructures with infrared silence, the hope clung on because it filled a deep psychological need. There's also the thrill of mystery unsolved. The longer Tabby's star resisted explanation, the more people leaned into alien theories. Our brains dislike uncertainty, so we fill the void with stories. The alien megastructure became a placeholder for ignorance, a narrative to hold on to while science caught up. And once the story took root, it was hard to uproot, even as evidence mounted for dust. This doesn't mean the alien hypothesis is useless. In fact, it serves an important function. By daring to suggest aliens, scientists, and the public test the boundaries of possibility. They ask, what would alien technology look like in our data? How would we distinguish it from natural phenomena? Even if Tabby's star is dust, the exercise prepares us for the day when a real signal might come. In that sense, the psychology of aliens pushes science forward. Spectral fingerprints of Tabby's star. Spectroscopy teaches us why a star dims, but brightness curves only show us when it does. Astronomers can look for absorption lines, which are tiny dips at certain wavelengths caused by atoms and molecules, by breaking sunlight into all of its colors. These are the marks that matter has left behind in space. It has been one of the most useful tools for Tabby's star because it has shown not only what is blocking its light, but also what it might be made of. When Boyajian's team and others began monitoring Tabby's star after the Kepler discoveries, they made sure to observe it in multiple wavelengths. During the famous 2017 dimming events, telescopes around the world gathered spectra as the star's light dropped. The results were striking. The dips weren't uniform across all colors. Blue light dimmed more strongly than red, a classic signature of fine dust grains scattering light. But the spectra revealed more than just dust. In some dips, astronomers detected narrow absorption lines of sodium and calcium, elements commonly found in rocky material. Their presence suggested that the dust wasn't just random interstellar haze, but had a mineral composition consistent with shattered planetary or cometary bodies. In other words, whatever was passing in front of the star carried the fingerprints of solid rocky material. This was a turning point. The alien megastructure idea struggled here, because artificial structures would block light equally across the spectrum and leave no chemical fingerprints. Dust, by contrast, left a messy but identifiable signature. The evidence tilted further toward natural explanations. Spectroscopy also allowed astronomers to test different dust models. The exact shape of the absorption across wavelengths depends on the size of the particles. For Tabby's star, the data pointed to submicron grains, tiny particles less than 1,000th the width of a human hair. These grains scatter light effectively in the visible range, but don't heat enough to produce detectable infrared radiation. This neatly explained the puzzling infrared silence. But the story didn't stop there. The spectral fingerprints varied from dip to dip. Sometimes the sodium lines were stronger. Other times they were absent. Sometimes the color dependence was sharp. Other times it was more muted. This suggested that the material blocking the star wasn't uniform. Different dips came from different clumps with varying compositions and grain sizes. Tabby's star wasn't hiding behind one smooth cloud, but behind a constantly changing patchwork of dust. Another possibility is that the dust storage is being fed by more than one process. Some clumps might be from the tails of comets, which are full of volatiles. Others may be from asteroids hitting each other and making silicate-rich rubble. Still others could be from a planet that is slowly breaking apart and losing matter as it orbits. The differences in the spectra can be explained by the fact that each source would give slightly different chemical fingerprints. Spectroscopy also ruled out some ideas. If the dips were caused by gas alone, astronomers would expect to see broad absorption features from hydrogen or other common elements. These weren't present at levels strong enough to explain the dimming. Gas alone couldn't do it. Solids had to be involved. Similarly, interstellar dust usually produces specific absorption bands, but Tabby's star's spectra didn't match those exactly, suggesting the dust was likely circumstellar. originating in the system itself. During some dips, the spectral lines of sodium and calcium were slightly shifted, a Doppler effect caused by motion. This suggested that the material was moving relative to the star at significant speeds, consistent with orbiting or infalling debris rather than distant, stationary clouds. Taken together, the spectra painted a picture of a system in turmoil. Something, perhaps multiple somethings, is creating streams of fine dust and mineral-rich fragments around Tabby's star. These clumps drift across our line of sight, dimming the star in irregular, unpredictable ways. Each dip is a new fingerprint, a new clue, another fragment of the puzzle. Astronomers see these spectral marks as valuable as gold. The talk goes from being based on guesses to having real proof. Dust isn't just a thought. It can be measured with elements and particle sizes that can be found. The fingerprints don't always answer the question, but they make it a lot easier to find the person. The star is still strange, but the dips in it aren't empty anymore. They have the chemical marks of space junk on them. The scientist's dilemma. Strange things are good for science, but not all strange things are beneficial. Astronomers were stuck with Tabby's star because it was too strange to ignore, but also too hard to explain. Each new finding added information, but none of them solved the problem. Scientists are taught to look for clear answers, so this presents a problem: how to study something that can't be explained without losing authority or giving up. From the beginning, researchers faced pressure. When Kepler first revealed the bizarre dips, natural explanations seemed inadequate. The data looked so abnormal that even respected astronomers like Jason Wright suggested alien megastructures as a possibility, if only as a thought experiment. That idea lit a fire in the media, and suddenly Tabby's star wasn't just an academic curiosity. It was a global headline. Scientists now had to balance cautious inquiry with a public hungry for sensational answers. The dilemma was stark. If they leaned too hard into exotic possibilities, they risked undermining their credibility. If they dismissed the star as unimportant, they might miss a chance at a major discovery. Many chose a middle path: admit openly that the phenomenon was baffling, explore natural explanations thoroughly, but never entirely shut the door on the exotic. This transparency was unusual in science, where researchers often avoid phrases like, "we don't know." Yet in this case, honesty became a strength. Admitting ignorance drew the public in rather than pushing them away. There was also a practical side to the problem. It's hard to find telescope time. Scientists have to defend every finding they make against other projects. Was it worth spending time and money on a flashing star when there were more interesting secrets to explore, like the atmospheres of exoplanets or galaxies far away? Some people said yes. Tabby's star was a priority because it was so special. For some, it was just an escape, a cosmic interest that wasn't going to lead to any big discoveries. Part of the balance act was figuring out how much work to put in. Then there was the issue of communication. When dust emerged as the leading explanation, some researchers worried about public disappointment. People had latched onto the idea of aliens. Would they lose interest if the truth was just dust? Scientists found themselves in the unusual position of managing expectations, reminding audiences that even mundane explanations can be extraordinary when scaled to cosmic levels. A single grain of dust on Earth is trivial. Trillions of grains, dimming a starlight years away, is awe-inspiring. The scientific process itself added tension. Each new dip was both an opportunity and a test. If the dips could be predicted, astronomers could prepare full campaigns with spectroscopy and multi-wavelength monitoring. But Tabby's star refused to cooperate. Its dimmings were irregular, unpredictable, sometimes shallow, sometimes deep. Scientists had to remain vigilant, coordinating global networks of telescopes, often at short notice. The star dictated the pace, not the researchers. Even interpreting the data posed dilemmas. Spectral fingerprints pointed to dust, but the dust didn't always behave consistently. Some dips showed strong chromatic dependence, others weaker. Some dips had calcium signatures, others didn't. Did this mean multiple processes were at work, or were instruments simply hitting their limits? Scientists had to walk a fine line between proposing bold new models and acknowledging uncertainties. The deepest problem might have been intellectual. As science moves forward, it turns riddles into answers. Still, Tabby's star seemed set on not giving up. What if the star doesn't give you a clear answer at all? What do scientists think about that? Some people felt bad about this. It feels like leftover business when a mystery isn't solved. It was freeing for some people. Not every question needs to have an answer. Some can just be left as questions to be answered. This duality between the desire for answers and the acceptance of mystery is the essence of the scientist's dilemma. Tabby's star embodies it perfectly. It is at once frustrating and exhilarating, humbling and inspiring. Each new observation narrows possibilities, yet the complete picture remains elusive. Dust, debris, interstellar curtains, shattered worlds, all remain plausible, none proven. And so, scientists continue to study the star, not because they expect a final revelation tomorrow, but because it represents the very heart of discovery. It is a reminder that science is not a straight path from ignorance to knowledge. It is a winding trail full of detours, false starts, and puzzles that may never be fully solved. Every wrong answer counts. Astronomers started coming up with ideas about Tabby's star as soon as it got attention. Every idea, dust, comets, broken planets, cosmic curtains, and megastructures, got people excited for a while. But then they ran into problems. It looks like this will fail at first glance. After years of research, there is still no clear answer. Science, on the other hand, doesn't waste time on wrong answers. Every answer that is thrown out makes the puzzle stronger, gets rid of the impossible, and brings us closer to the truth. Take the comet hypothesis. At first, it was appealing. A swarm of comets passing in front of the star could create irregular dips of varying depth. But careful modeling showed that the number of comets needed was absurd. Hundreds of giant ones, perfectly aligned with our view. Infrared observations also failed to detect the expected heat from so much icy debris. The comet idea collapsed, but in doing so, it clarified the scale of the problem. Whatever caused the dips had to be larger, stranger, or less dusty than comets could provide. The alien megastructure theory drew global headlines, but the infrared silence dealt it a blow. Any technology intercepting that much starlight would re-radiate waste heat, glowing like a beacon in the infrared. Spitzer saw nothing. While this didn't disprove the idea completely, it forced scientists to acknowledge the physical constraints of energy use. Even if aliens exist somewhere, the data here pointed elsewhere. The wrong answer reminded researchers how to distinguish science fiction from science. The idea of a shattered world also caught on. A world that is torn apart by tides could leave behind dust clouds big enough to block 20% of starlight. But once more, IR scans did not find the glowing dust that would be expected from such damage. This bad answer didn't end the case. Instead, it showed how strange Tabby's star really is. Even huge impacts, which can explain dimming in some other systems, don't quite work here. Each wrong answer taught scientists what isn't happening. The star is not a pulsating variable because its underlying brightness is stable. It's not an eclipsing binary because spectra reveal no companion star. It's not hidden behind a massive interstellar nebula because neighboring stars don't share the same dimming. One by one, familiar categories were eliminated. Far from being wasted effort, each misstep narrowed the field of possibilities. Wrong answers also drive innovation. To test the comet idea, astronomers developed new models for dust production and scattering. To test the alien megastructure idea, SETI refined its search strategies, scanning Tabby's star for faint radio signals. To test the planetary debris model, telescopes honed their infrared sensitivity. Even when the hypotheses fell short, the tools and techniques improved. Science advanced, not in spite of the mistakes, but because of them. Scientists didn't want to say they didn't know something in public, but Tabby's star made them. Researchers showed how the process works by looking at wrong answers in a public way: suggest, test, reject, and improve. The public could see science make mistakes in real time, showing that getting the wrong answer is part of the trip and not a bad thing. In fact, the trend looks a lot like the past. Before they were known as neutron stars, pulsars were called LGM, which stands for Little Green Men. Astronomers didn't understand what quasars were for years before they realized they were active galactic centers. People used to think that even black holes were just interesting mathematical ideas. Before a big step forward, there were a lot of wrong replies. This book, Tabby's Star, may be the newest in that bloodline. It's a warning that today's puzzle could become tomorrow's textbook chapter. The importance of wrong answers extends to education. Teachers use Tabby's Star as a case study in how science really works. Students see that failure is not the end, but the middle of discovery. Each wrong turn maps the terrain of the unknown, showing where the boundaries lie. The century-scale fade debate. Tabby's star is exciting when it goes down in the short term, but the long term may be even stranger. Early on in the investigation, scientists thought the star might not only be flashing, but also slowly dying out over decades or even centuries. If this is true, it would mean that the system is changing over a much longer period of time than a comet moving by or a short dust cloud drifting by. But it's hard to prove that there is such a trend, and the century-scale fade is still one of the most controversial parts of the story. The claim began with old glass photographic plates. For more than 100 years, astronomers at Harvard and other observatories photographed the night sky, creating a vast library of star images. By digitizing these plates, modern researchers can measure how bright a star appeared in the early 1900s compared to today. Bradley Schaefer, an astronomer at Louisiana State University, analyzed plates containing Tabby's star and found a steady dimming of about 0.16 magnitudes per century, roughly a 15% decline in brightness. That was stunning. Stars like Tabby's, middle-aged F-types, are expected to shine steadily for billions of years. They don't drift downward in brightness on human timescales. If Schaefer's result was correct, it meant something large-scale was blocking the light or altering the star's output over generations. It added weight to theories about massive dust veils or long-term planetary disruption. But not everyone was convinced. Photographic plates are notoriously tricky. Their sensitivity varies, emulsions degrade with age, and exposures differ. Even digitization can introduce biases. Critics argued that the apparent fade could be an artifact of the data rather than a real astrophysical effect. Another group reanalyzed the plates using different methods and concluded the long-term dimming was less clear, perhaps even non-existent. The debate escalated as more datasets were brought in. The American Association of Variable Star Observers, AAVSO, had decades of brightness records collected by amateurs. Some showed hints of long-term fading, others didn't. More recent precise data from missions like Gaia suggested only small changes, if any, over shorter timescales. The picture became muddled. If the century fade is real, it changes the story dramatically. Sudden dips could be explained by comets, dust, or planetary debris, but a slow fade implies a persistent curtain of material drifting into place. It would mean we're not just catching isolated events, but watching a system evolve in slow motion. Some models imagine a giant cloud of dust or debris on a long orbit, gradually thickening along our line of sight. Others suggest that Tabby's star could be shedding material, creating its own dimming veil. If the fade is not real, then the focus shifts back to short-term dynamics. Clumps of dust replenished by collisions, comet showers triggered by the distant companion star, or other localized events. The dips remain fascinating, but the century-long trend would not need explaining. That's why the debate matters. It's not just about a number on a graph. It's about whether the mystery is episodic or evolutionary. Recent events make us more likely to be cautious. In the last 10 years, high-precision photometry has shown dips and small changes, but not a clear, smooth drop. The trend isn't very clear if the star is going out. Some scientists say Schaeffer's century fade was exaggerated and was just a false impression caused by bad data. Some people say that even small fades and random dips together show a more detailed story than just dust. For scientists, this debate illustrates the challenge of long-term astronomy. Human lifespans are short compared to stellar processes. Reconstructing century-scale trends requires trust in historical data, which was never collected with this mystery in mind. The glass plates were invaluable, but they weren't perfect, and the uncertainty may never be fully resolved. Astronomers have had to think about two different time periods at the same time because of Tabby's star. Chaotic dips, which are rapid drops in light that last for days or weeks, happen on the short scale. We might have a fade that lasts for decades in the long term. Part of the ongoing task is to find a balance between these two points of view: fast and slow, sharp and steady. The star's neighbors. To see if Tabby's star really is one of a kind, all you have to do is look around it. Crossing our line of sight would be a cloud of cosmic dust or gas. Stars nearby in the same area of the sky should also get fainter. A nearby nebula wouldn't just hide in front of Tabby's star if it were to blame. One important step in solving the puzzle was to talk to the neighbors. Kepler's original field of view contained thousands of stars, many of them within a few arc-minutes of Tabby's star. Astronomers examined their light curves carefully. None showed the same bizarre dips. Some had small fluctuations, typical of variable stars, but nothing like the dramatic plunges that defined Tabby's star. This was the first clue. Whatever was happening seemed to be confined to this star alone. The lack of similar dimming in nearby stars argued strongly against the interstellar curtain hypothesis. A dust cloud between Earth and Tabby's star should also affect stars just a little to the left or right. But those stars look normal. That meant the obstruction wasn't floating halfway between us and them. It had to be local to Tabby's star itself. The focus then turned to companions. A lot of stars are found in groups of 2 or 3. Tabby's star might have a secret partner who is adding to the chaos. Precision readings by Gaia showed that it does have a faint red dwarf partner that is about 900 astronomical units away. That's so far away that it would take light more than a week to cross. This faraway neighbor isn't close enough to directly block light, but its weight could make it so. More than 1 million years, the dwarf star could stir up comet stores or outer debris bands, pushing icy bodies toward the main star. Those bodies could make the dust clouds that cause dips if they break apart. Astronomers also searched for closer companions that might have been missed. Spectroscopy and radial velocity measurements looked for wobbles in the star's motion that would reveal a hidden partner tugging on it. None were found. Tabby's star appears to be solitary, except for its distant red dwarf neighbor. That rules out many binary star explanations, like eclipses from a close companion. The neighborhood analysis extended even farther. Was Tabby's star located in a particularly dusty region of the galaxy? Surveys of interstellar extinction, the amount of light absorbed by dust along different sightlines, showed that while the Cygnus region has normal amounts of dust, it isn't unusually thick or patchy at Tabby's star's location. This reinforced the idea that the dips must come from circumstellar material rather than distant veils. It's exciting that scientists also looked to see if Tabby's star had any infrared neighbors that they might have missed, like brown dwarfs or dusty disks. Infrared scans didn't find any important sources close to the star. Its neighborhood looked clean, which put all the attention on the star itself. The search for neighbors wasn't just about eliminating interstellar dust, it was also about context. If dozens of nearby stars had shown strange dips, astronomers might have classified Tabby's star as part of a new group of variable stars. But the absence of similar behavior highlighted its uniqueness. Out of all the stars Kepler monitored in that patch of sky, only one stood out. Still, The presence of the distant red dwarf companion keeps the door open for dynamical explanations. Systems with wide binaries often show unusual behavior because the secondary star perturbs cometary clouds. Our own Sun's Oort cloud may have been shaped by passing stars billions of years ago. In Tabby's star's case, the red dwarf could serve as the long-term trigger, slowly destabilizing icy reservoirs and feeding dust into the inner system. The dust and debris ideas work well with this kind of secondary effect. It explains how new matter could keep adding to the clouds that cause dips, even though the star is fully grown and shouldn't have much left over from when it was first formed. Without a cause, it's hard to understand why dust would stay around. With a faraway friend, the scene makes more sense. Could Tabby's star be common? Tabby's star looked like the kind of once-in-a-lifetime find that stands out in the history of astronomy at first glance. But as studies get bigger and cameras get better, it makes sense to wonder if Tabby's star is really the only star of its kind, or if there are more like it in the data. If the strange dimming is typical of stars in a larger group, then what seemed unusual might be normal, just not spotted very often. Kepler monitored over 150,000 stars, and in that vast database, Tabby's star was the one that stood out. No other star showed dips as deep, irregular, and unpredictable. That suggested rarity. But astronomers have since combed through data from Kepler, TESS, and other surveys, looking specifically for Tabby-like behavior. The results are intriguing. Several candidates have emerged. Some stars show erratic dimmings, though not as extreme. RZ Piscium, for example, dims irregularly by up to 10%. Other stars in Kepler's catalogue, such as KIC 125575548, display dips caused by disintegrating planets, and EPIC 2042789116 showed a dramatic dimming event of over 60%. While none match Tabby's star perfectly, they suggest that irregular dimming is not unique, even if the scale differs. Large-scale surveys like ASUS-SN, All-Sky Automated Survey for Supernovae, and ZTF, Zwicky Transient Facility, are helping answer the question more systematically. These projects scan millions of stars, looking for brightness changes. Among their results are dozens of stars with peculiar dips, some of which resemble Tabby's star in shape if not in depth. This hints at a continuum. Tabby's star is the extreme case on a spectrum of odd dimmers. But rarity doesn't always mean uniqueness. Consider pulsars. The first one discovered in 1967 seemed like a bizarre anomaly, even nicknamed LGM1 for little green men. Now we know there are thousands. The same might be true here. Tabby's star could be the first identified in a new class of dusty, unstable systems that will grow in number as our tools improve. At the same time, the rarity so far is telling. If stars like Tabby's were common, Kepler and TESS should have found many more. The fact that only a handful of candidates exist suggests that whatever process is happening must be unusual. Planetary destruction, massive dust replenishment, or rare orbital dynamics could all produce the right conditions, but only rarely. That balance between rarity and possibility keeps the debate alive. Astronomers also wonder if we might be missing others simply because of perspective. For a dip to be visible, the dust or debris must cross directly between us and the star. If the material orbits at a slight tilt, it could miss our line of sight entirely. That means there may be many Tabby-like systems out there, invisible to us because we don't have the right viewing angle. In that sense, Tabby's star might not be rare at all, just rarely aligned. Another challenge is detection limits. Kepler and TESS are powerful, but they don't catch everything. Shallow dips, short events, or irregular ones in faint stars can be missed or misclassified. As machine learning improves, astronomers are reanalyzing old data with algorithms trained to spot unusual patterns. Already this has uncovered stars with subtler versions of Tabby-like flickers. The more we look, the more the universe surprises us. If Tabby's star is part of a larger group, that has exciting implications. It would mean that dust clouds, shattered planets, or other strange processes are more common than we thought. It would reshape our understanding of how planetary systems evolve over billions of years. It might even suggest that destruction and instability are normal phases in a star's life cycle, not rare exceptions. Tabby's star, on the other hand, becomes more important if it stays unique even after decades of polls. If a single event causes new physics or astrophysics models, it can change the way courses are written. The result is important no matter what. A similar group of Tabby stars would help astronomy learn more, and a single case would show how different and random the universe is. The role of the interstellar medium. Scientists were first puzzled by Tabby's star's strange dimming. Some asked a simple question: what if the issue isn't with the star itself, but with the space between us and it? It's not true that the universe is a vacuum. The interstellar medium is made up of gas, plasma, and dust that can scatter and absorb light. It is in between the stars. Could moving clouds of this stuff work like a cosmic filter to explain the bumps and dips we see? The interstellar medium is patchy. In some regions, it's so thin you could travel trillions of kilometers without hitting a single dust grain. In others, it thickens into filaments, clouds, or dark nebulae that block entire regions of the Milky Way. These dusty curtains redden starlight and dim distant objects, an effect astronomers call extinction. It's a well-studied process, but usually it operates smoothly across many stars in the same region. If Tabby's star were behind such a cloud, neighboring stars should also appear dimmed. They don't, which immediately weakens the case. Still, the possibility isn't dismissed entirely. The interstellar medium is not uniform. It can form small, dense knots of dust only a few astronomical units across. If one of these knots drifted directly into our line of sight to Tabby's star, it could dim its light without affecting nearby stars. Such knots are difficult to detect because they're tiny compared to galactic scales, and they may not glow strongly enough in the infrared to stand out. Spectroscopy offers tests. Interstellar dust and gas leave distinctive absorption lines in a star's spectrum. Sodium and calcium, for instance, often betray the presence of foreground material. In Tabby's star, astronomers have indeed seen absorption features, but they don't fully account for the depth or irregularity of the dips. The patterns suggest that at least some of the material must be circumstellar, belonging to the star's own environment, rather than distant interstellar dust. Motion is a part of another point of view. As we move through space, the interstellar medium is formed by the galaxy winds and the remains of supernovae. If cosmic clouds were making Tabby's star less bright, we might expect a smoother, longer-lasting fade as the cloud moves, instead of short, sharp dips that last only days. Issues arise when time frames don't match up. This could explain the fade over 100 years, but the short-term drops don't look like they could be caused by clouds far away. Yet the idea remains attractive because it avoids more exotic explanations. Dust in interstellar space is a known quantity. If enough of it happens to align just right, it could mimic the bizarre flickering we see. Models have been built exploring this scenario, showing how filaments of dust with varying densities could create patterns like Tabby's dips. While the models don't fit perfectly, they remind us that sometimes the strangest answers lie not in the star itself, but in the foreground. The debate over the interstellar medium also ties into Gaia's results. By mapping extinction across the galaxy, Gaia has given astronomers a clearer picture of how much dust lies between Earth and Tabby's star. The verdict? Moderate amounts, but not enough to explain the deepest dips. This doesn't rule out tiny local knots, but it suggests they aren't the whole story. There's also the hybrid possibility, a mix of circumstellar and interstellar dust. Perhaps Tabby's star is shedding material, and as that material drifts outward, it merges with interstellar filaments. The result would be a layered curtain, some close, some far, each contributing to the flickers and fades we observe. This would explain why some dips show chromatic dependence, pointing to small nearby grains, while others resemble the smoother effects of interstellar extinction. Astronomers use the interstellar medium theory to keep things in perspective. There are many layers of cosmic gas that let us see the world. Starlight can be bent or turned red by the galaxy's dusty tunnels, just like Earth's skies can do to the sun. Tabby's star might not be acting up at all. It could just be unlucky and stuck behind a moving veil of cosmic haze. A lot of experts agree that this can't be the whole story. The dips are too deep, too irregular, and too special to one star for cosmic matter to fully explain them. Most likely, the medium is just an extra part of the system that makes it more complicated. There is already a lot of dust and junk close to the star. It's not a secret which one to choose. It's how to figure out how both of them work together. A star out of place? Tabby's star is a normal F-type main sequence star, which means it is bigger and hotter than the Sun, but not out of the ordinary. It looks like it should be one of the millions of stable suns in our galaxy. Still, the way it acts is not at all normal. This makes me wonder if Tabby's star might not be where it should be. It's possible that the strange flickering isn't just caused by dust or debris, but by the star itself not fitting nicely into the group that would be expected of it. Astronomers rely on the Hertzsprung-Russell diagram, a kind of stellar map that plots stars by brightness and temperature. Tabby's star sits right where it should, among other middle-aged F-type stars. It isn't too young, it isn't too old, and its spectrum shows no obvious anomalies. By every standard classification metric, it is textbook normal. That makes the irregular dips even more puzzling. Why would a star that looks so ordinary act so extraordinary? It's possible that the classification hides small differences. For instance, the amounts of chemicals in some stars aren't like those in other stars, so they don't fit into broad groups. If Tabby's star has different amounts of metallicity, more or less elements heavier than helium, it might change how its outer layers behave or how dust forms around it. Spectroscopy has shown that it is pretty normal so far, but small differences in the makeup could still be important. Another idea is that Tabby's star might not be fully alone. Its faint red dwarf companion, located hundreds of billions of kilometers away, may seem too distant to matter. But gravitationally, even a small tug over long timescales can destabilize planetary systems. If the star system formed in an unusual configuration, perhaps with more companions that were later ejected, it might carry scars we can't see directly. Its current instability could be the legacy of a chaotic past. There's also the question of the galactic environment. Stars don't live in isolation. They orbit the Milky Way, passing through regions with different densities of interstellar material. If Tabby's star originated in a denser cluster or migrated from another region of the galaxy, its current surroundings might not match its evolutionary history. A star out of place in this sense could bring unusual debris with it. Comet clouds perturbed long ago, still raining inward centuries later. Some researchers have even speculated that Tabby's star might be part of a rare class of quasi-variable F-stars, where subtle instabilities in the outer envelope occasionally trigger strange dimming. Most stars in this range are well behaved, but perhaps a small fraction develop quirks we don't yet understand. Tabby's star, being the first we've studied in such detail, could simply be the unlucky or lucky example that exposed the phenomenon. Gaia's data helps here. Its precise measurements confirmed that Tabby's star lies about 1,470 light-years away and shines with the brightness expected of an F-type star at that distance. It isn't secretly a giant masquerading as a smaller star, nor a compact object throwing off unusual signals. It sits exactly where it should on the stellar map, and yet it refuses to act like its peers. The out-of-place question is so interesting because of the tension between classification and behavior. If Tabby's star really is the only one of its kind among F-types, then either we're not putting stars into the right categories, or this one has had a strange past that makes it stand out. In either case, it makes us think about how clean we think the world is. Astronomers are careful not to go too far with this angle. After all, classification systems are strong, and one strange thing doesn't change decades of knowledge about how stars work. But oddities are important. Pulsars, quasars, and brown dwarfs were all stars that didn't look like other stars. Each made us rethink the groups of stars. If Tabby's star is also out of place, it might grow one day. Disintegrating planets. When astronomers looked for analogies to explain Tabby's star, they didn't have to look far. Kepler had already revealed stars with dimming patterns caused by something even stranger than dust clouds, planets falling apart. These disintegrating planets provide a natural laboratory for understanding how solid bodies break down under stellar heat, and they may hold clues to the mystery of Tabby's star. One of the most famous examples is KIC 125575548. This star shows dips in brightness every 15.7 hours, consistent with a small planet orbiting extremely close. But the dips aren't uniform. Sometimes they're deeper, sometimes shallower, and sometimes they vanish. The best explanation is that the planet is literally evaporating. Intense stellar radiation blasts material off its surface, creating a dusty comet-like tail. As the planet circles the star, the changing shape of the tail produces irregular dimming. Another case is KOI 2700b, which also shows variable transit depths linked to a disintegrating body. These planets are tiny compared to Earth, closer to the size of Mercury or smaller, but they demonstrate that planetary destruction is not rare. When worlds wander too close to their stars, they don't survive long. Instead, they crumble into clouds of dust that obscure light in unpredictable ways. What makes these examples relevant is the way dust behaves. The tails of disintegrating planets are made of micron-sized grains, just like the particles suspected at Tabby's star. They scatter blue light more than red, creating chromatic dips. They produce little to no infrared glow because the grains are small and cool quickly. In short, they tick many of the same boxes. The physics of disintegration matches much of what we see at Tabby's star. But there is one important difference: the size. When a planet is breaking apart, the dips are generally only 1% to percent deep. Tabby's star, on the other hand, falls by as much as 20%. For that depth to be repeated, the dust cloud would have to be huge, much bigger than the tails of planets that are known to be breaking apart. Some researchers think this could happen if the object in question wasn't a small rock, but a bigger one, like a super-Earth or even a planet the size of Neptune that was broken up by the tides. A disaster of this magnitude could create enough debris to block out a lot of stars. The lesson is that destroying the world is a real process that can be seen. We have caught stars as they are destroying their worlds and leaving behind dusty tracks. It's possible that Tabby's star is a tenfold extreme case of the same thing. The dips might not be happening by chance. They could be part of a long-term process, a planet breaking apart orbit by orbit until there is nothing left but dust. Spectroscopy supports this link. At Tabby's star, dips sometimes show sodium and calcium absorption lines, elements expected in rocky material. This matches what disintegrating planets shed as they crumble. The fingerprints align, though again, the scale is much larger. Instead of one tiny planet dissolving, Tabby's star may be processing multiple bodies, or the remains of a massive collision. Even if the exact mechanism differs, disintegrating planets provide a framework. They show how dust clouds can form, how they scatter light, and how they evolve over time. They also demonstrate the importance of geometry. The tails often create asymmetric dips, with a sharp entry and a slow fade as the dust trails behind. Tabby's star's dips don't always match this shape, but some do, hinting that similar physics may be at work. The similarity is both calming and terrifying for astronomers. It's comforting to know that Tabby's star isn't the only one who experiences dusty weakening. It's scary because getting the phenomenon to Tabby's level would take very special circumstances, and maybe even more than one process going on at the same time. Still, the range of options from small planets breaking apart to large-scale dimming is wide. Could rings or megadisks explain it? When Kepler first showed the huge dips in Tabby's star, one of the first natural thoughts that came to mind was that something big and structured might be orbiting nearby. What if the culprit wasn't comets or dust clouds moving aimlessly, but a huge ring system or even a megadisk that goes around the Sun. In science, rings and disks are common shapes. But when they are blown up to the size of the universe, they could block light in very strange and dramatic ways. The ring hypothesis grew from analogies to Saturn. Saturn's rings are broad, thin, and composed of billions of icy particles. When exoplanet hunters discovered J1407b, a possible giant planet with an enormous ring system, astronomers realized that rings could sometimes produce dips in brightness far larger than those caused by planets alone. J1407b's rings are estimated to be 200 times the size of Saturn's, big enough to block a star's light for days. If Tabby's star had a planet with a ring system on a tilted orbit, it could, in theory, explain some of the deep dimming events. But troubles show up. Rings usually make shapes that are structured and can be repeated. As they circle, the same shape comes back, which makes the dips predictable. Tabby's star, on the other hand, has not shown any regularity. The size and time of its dips are all over the place. That makes it unlikely that there is a single stable ring system. Still, shadows could be wavy if the ring is broken or changing, possibly because of a planet that is breaking apart. The megadisk idea is broader. Instead of rings around a planet, imagine a huge disk of material encircling the star itself. Young stars often have such disks, protoplanetary disks where planets form. These disks block light and create variability. But Tabby's star is not young. It's a mature main sequence star that should have cleared out its disk long ago. For it to still host a massive megadisk, something unusual must have happened, such as the recent disruption of a giant planet or the capture of material from another body. Disks also tend to leave infrared signatures. Dust in a disk absorbs starlight and re-radiates it as heat. Yet Tabby's star is silent in the infrared. That silence suggests that if a disk exists, it must be composed of very fine, cool dust spread thinly enough to evade detection, while still producing dramatic dimming along our line of sight. A delicate balance, possible, but not easy to maintain. Despite these challenges, the ring and disk scenarios remain attractive because they involve structures we already know exist elsewhere. They don't require exotic new physics or speculative aliens, just scaled-up versions of processes already observed. They also fit with the hints of sodium and calcium in the star's spectra, consistent with rocky or icy material ground into dust. Some researchers propose hybrid models. Perhaps a giant planet was shattered, creating both a ring system and a debris disk. Over time, the structures evolve, clumping and dispersing, producing the irregular dips we see. In this view, Tabby's star is not hosting a single stable object, but a chaotic aftermath of planetary destruction, with rings and disks blending into a complex shadow-casting environment. There are tests based on what you see. If you watch a stable ring system for a long time, it should finally show periodicity. A disk should show small changes in color between dips that can be seen with very accurate spectroscopy. The data we have so far points to dust, but it doesn't completely rule out bigger structures. Astronomers hope to get a better look at the shape with JWST and other future telescopes, looking for signs of rings or megadisks. The important thing about this line of study is that it reminds us that planetary systems can change quickly and violently. When we think of stars, we usually picture them with neat orbits and straight lines, like in textbook models. Planets and moons can collide, though, and disks can stay around for a long time after their projected lifetimes are over. Tabby's star might just be telling us that chaos happens more often than we think. Lessons for exoplanet science. When scientists first set up Kepler, their goal was simple: to find planets by looking for predictable drops in the brightness of the stars. The project was a huge success, finding thousands of exoplanets and changing the way we think about planetary systems. It was shown by Tabby's star, though, that not all dips fit nicely into the planet box. It's possible for light curves to be so strange that they change the rules of the game. Tabby's star's secret has become one of the most important things to learn about other planets in this way. The first lesson is humility. Before Tabby's star, astronomers thought they had a good handle on stellar behavior. Variable stars had known patterns, planets produced repeating signals, and dust disks showed clear infrared excess. Tabby's star broke those expectations. It proved that even ordinary F-type stars can surprise us with behavior no model had predicted. For exoplanet science, this was a reminder not to assume neat universes. Messiness is part of the picture. The second lesson is the importance of anomaly hunting. Kepler's automated pipelines were designed to detect periodicity, not irregular chaos. Tabby's star nearly slipped through the cracks until citizen scientists flagged it. That highlighted the need to look beyond the obvious. Exoplanet science now invests more in outlier analysis, ensuring that rare one-off events are studied rather than dismissed as noise. After all, some of the biggest breakthroughs in astronomy, like pulsars and quasars, began as anomalies. The third lesson is the power of multi-wavelength observations. Tabby's dips showed chromatic dependence, with blue light dimming more than red. That detail pointed directly to dust and ruled out opaque bodies. Exoplanet researchers took note. Studying transits in multiple colors isn't just optional, it's essential. The practice is now standard in exoplanet follow-up campaigns, helping distinguish between genuine planets and false positives caused by stellar activity or dust. The fourth lesson is about time. Planets follow orbits that repeat. Dust clouds, shattered worlds, and disintegrating planets do not. Tabby's star forced exoplanet scientists to expand their toolkit from periodic searches to irregular monitoring. Missions like TESS and upcoming surveys like the Vera C. Rubin Observatory are now better prepared to capture transient and non-repeating phenomena. Exoplanet science, once focused on stability, now embraces instability as part of planetary evolution. The fifth lesson involves collaboration. Tabby's star became a global project. Crowdfunding, amateur astronomers, and professional networks like Las Cumbres worked together to monitor the star. That model has since been applied elsewhere. When strange transits appear, coordinated campaigns mobilize worldwide. Exoplanet science is increasingly community-driven, blending professional rigor with citizen participation. The sixth lesson is about planetary destruction. Disintegrating planets, collisions, and dusty tails are no longer theoretical oddities. They are observed realities. Tabby's star highlighted just how violent planetary systems can be. For exoplanet science, this shifted the narrative. Planets aren't static. They live and die, crumble and collide, leaving behind dusty signatures. Understanding these processes is now as important as finding stable worlds. Another lesson is methodological. Tabby's star revealed the importance of revisiting archival data. The century-scale fade debate, whether real or not, drew from glass plates dating back to the early 1900s. Exoplanet science has since embraced this approach, mining historical data to search for long-term variability in stars. The past, it turns out, can hold clues to planetary fates. Exoplanet scientists learned how to talk to the world through Tabby's star. The alien megastructure theory may not have been based on facts, but it caught people's attention. This got a lot of attention, which paid for new observations and sparked interest in astronomy. The study of extrasolar planets taught us that secrets are chances to communicate and learn new things. Even when the answer is dust, the journey can inspire a new generation of explorers. Why the mystery still matters. By now, most astronomers lean toward dust as the explanation for Tabby's star. Fine grains scattered across its system, perhaps replenished by shattered comets or disintegrating planets, account for the color-dependent dips, the lack of infrared glow, and the irregular patterns. On paper, the mystery looks nearly solved. And yet, the fascination lingers. Why? Because Tabby's star is more than a puzzle about dust. It is a reminder of why astronomy matters at all. First, it shows us the limits of our knowledge. For centuries, we thought we understood how stars behave, steady, predictable, governed by well-known physics. Then along came Tabby's star, an ordinary F-type star that refused to play by the rules. It forced astronomers to admit uncertainty, to say aloud, "We don't know," That honesty matters. Science advances not by pretending to know everything, but by confronting what it cannot yet explain. Second, it demonstrates the power of curiosity. A flicker in the sky could have been dismissed as noise. Instead, citizen scientists flagged it, researchers investigated it, and the world tuned in. That chain of events shows how curiosity connects people across backgrounds, professionals, amateurs, journalists, and the public, around a shared sense of wonder. Tabby's star reminds us that the universe belongs to everyone, not just those with telescopes. Third, it highlights the value of persistence. For nearly a decade, astronomers have watched the star, gathering spectra, analyzing dips, and debating models. Every wrong answer has been a step forward, narrowing the possibilities. The process may seem slow, but it reflects the heart of science, patient, methodical, and relentless in the pursuit of truth. The star's mystery still matters because it models how discovery actually works. Fourth, it keeps the door open to the unexpected. While dust is the leading explanation, anomalies remain. The century-scale fade, the variability between dips, the lack of a simple repeating mechanism. These gaps remind us not to close the book too quickly. Astronomy has a history of surprises. Pulsars mistaken for aliens, quasars dismissed as noise, black holes once thought impossible. Tabby's star may yet hold a twist we haven't seen. Fifth, it fuels imagination. Even if aliens are off the table scientifically, the idea of an alien megastructure sparked global conversations about what advanced civilizations might look like. It inspired novels, documentaries, and podcasts. It made people dream bigger, not about UFOs, but about the cosmic scale of possibility. That cultural impact is valuable in itself. A star 1,470 light-years away made humanity stop and wonder, and that wonder still matters. Sixth, it ties into larger questions. Studying Tabby's star isn't just about one system. It's about planetary evolution, dust dynamics, and stellar environments. Each insight feeds into exoplanet science, galaxy surveys, and the search for life. By probing the strange, we improve our understanding of the ordinary. The mystery matters because it advances science across the board. Seventh, it shows the importance of collaboration. From crowdfunding campaigns to international telescope networks, the investigation of Tabby's star has been a team effort. It demonstrated that when professional science opens its doors to the public, incredible things happen. Thousands of small contributions, donations, observations, discussions added up to a global research project. That model will inspire future studies of other anomalies. Without a conclusion, Tabby's star's story stays unfinished, a flickering mystery that serves as a reminder that the universe is much weirder than we think. Whatever the answer is, dust, junk, or something we haven't even thought of yet, this star has already done something amazing. It has made us wonder. Discoveries aren't just about finding answers, they're also about the questions that keep us looking up. Join us as we explore the universe by giving us a like, subscribing, and leaving a message below. Here on Beyond Horizons, both the world and us are always finding new secrets.